Hello there, and welcome to the Cosmographer. The black hole photographed in 2019 has an event horizon wide enough to hold the entire solar system 8 times over, and every genuinely strange thing about it sits on the other side of that boundary. Number 7 on this list is an argument published by 4 physicists who wanted to be wrong that the boundary is not a doorway at all, but a sheet of fire. Number 6 is a careful measurement of how much room is inside an object 25 million kilometers across, and the answer keeps growing while the outside stays exactly the same. Number 4 is a surface where the entire remaining future of the universe outside arrives in a single instant. And number 1 is not an object. 10 entries, ordered not by how alarming they sound, but by how far each one reaches back out of the hole. Get comfortable and settle in. If you enjoy falling asleep to the long walk through questions nobody has answered, a quick like and subscribe helps this channel reach more curious minds like you. Because by the time we reach number 1, the word inside will have stopped meaning what it means right now. Let's begin at number 10. Number 10. The ring of trapped light. There is one category of object in physics that is believed to exist, described in detail, photographed twice, and known to be unobservable on the inside as a matter of principle rather than as a matter of engineering. Everything else in the universe can in principle be visited and reported on. Send a probe far enough, wait long enough, build an instrument sensitive enough, and eventually the thing gives up its interior. The interior of a black hole does not work that way. The geometry is arranged so that no signal produced inside has any path that leads back out. Not a difficult path. Not an expensive one. No path at all. That is what makes this list possible, and it is also what makes it strange. When a region cannot be examined, the only tools left are mathematics and consistency. And what mathematics has produced over the last 60 years, working from equations that have passed every test anyone has designed for them, is a series of answers that get progressively harder to live with. This list counts down 10 of them. The ranking is not by how alarming each one sounds. It is by how far the consequence reaches back out of the hole. At number 10, the strange thing is outside the horizon entirely, and it has already been photographed. By the middle of the list, the strange things are behind the horizon, reachable only by falling in and never reporting back. At number 4, the strange thing is a surface where physics stops being able to predict anything at all. At number 2, the strange thing rewrites what the ending of a black hole even is. And at number 1, the strange thing is a proposal under which the inside of a black hole is not a region of space at all, which raises a question about where the listener is currently sitting. Some of these are established. Some are contested. 3 of them have been photographed or detected. 4 are direct consequences of general relativity that no working physicist disputes. 3 are conjectures whose own authors describe them as conjectures, and this episode will say so every time, because the honest version of this subject is more interesting than the confident version. We begin at the outside, with something that has been imaged twice, and that is still one of the strangest structures in the sky. At a particular distance outside every black hole that is not spinning, gravity bends the path of light by exactly enough that the light travels in a circle. The distance is 1.5 times the radius of the event horizon, and the surface it defines is called the photon sphere. A photon that arrives on precisely the right trajectory does not fall in and does not escape. It orbits the way a satellite orbits, except that the thing in orbit is light itself, and the orbit is maintained by the curvature of space rather than by any force acting on a mass. The important detail is that these orbits are unstable. A photon in the photon sphere is balanced the way a pencil is balanced on its point. The slightest deviation compounds rather than corrects. A photon that arrives a hair inside the critical trajectory spirals inward and is lost. A photon that arrives a hair outside it loops once, or twice, or 50 times, and then spirals back out and continues on its way, carrying with it a picture of everything it passed while it was going around. Which means that what surrounds a black hole is not a ring of light. It is a nested infinity of rings, one inside the other, each made of photons that went around exactly one more time than the ring just outside it. Consider what that implies. Light takes time to travel. A photon that circled the black hole twice before leaving departed from its source earlier than a photon that circled once, because it spent longer in transit. A photon that circled 100 times departed earlier still. So the rings are not merely nested in space. They are nested in time. The outermost bright band is a picture of the sky as it looked a moment ago. Just inside it is a picture of the same sky from earlier. Inside that, earlier again. The sequence continues inward without any natural stopping point, converging on an image of the universe as it looked when the black hole formed. It is a ring of images of a sky that no longer exists, and it is sitting there, in the data, at the edge of every black hole in the universe. The reason nobody has resolved that stack is a matter of thickness. Each successive ring is thinner than the one outside it by a very large factor. For a black hole that is not rotating, the factor is about 535. So the second ring is roughly 500 times thinner than the first, the third is 500 times thinner than the second, and by the fourth or fifth, the structure is far below the resolving power of any instrument that has ever been built, or that anyone currently knows how to build. One further complication, which the images cannot yet see, but which is present in every real black hole. Everything described so far assumes a black hole that is not rotating, and no black hole in the universe is not rotating. When the object spins, the single photon sphere splits. Light traveling with the rotation can hold its orbit much closer in than light traveling against it, because the rotation is dragging the space it moves through. The result is not a sphere at all, but a shell of possible orbits, thicker on one side, with a range of radii instead of a single radius. James Bardeen worked out the consequence for the appearance of the shadow in 1973, 46 years before the first photograph. A spinning black hole casts a shadow that is slightly flattened on the side where the rotation is coming toward the observer. The effect is small, and the current images are not sharp enough to measure it, which means one of the cleanest available tests of the theory is sitting just past the edge of what has been resolved. The scale of the object those rings surround is worth establishing before we go further, because every number on this list is meaningless without a comparison to sit beside it. The black hole at the center of the galaxy Messier 87 has a mass of about 6.5 billion times the mass of the Sun. Its event horizon is roughly 38.4 billion kilometers across. That number does not communicate anything on its own, so here is the comparison. The distance from the Earth to the Sun is about 150 million kilometers. The distance from the Sun to Neptune is about 4.5 billion kilometers. The horizon of that black hole is more than 8 times the diameter of Neptune's orbit. The entire solar system, including the Kuiper belt and everything in it, would fit inside that boundary several times over, with room to spare. The shadow the object casts is larger still, because the capture region for light extends beyond the horizon. Light passing within about 2.5 times the horizon radius is caught and does not come back. So the dark disk an observer sees is roughly 5 times the width of the horizon itself, and the bright ring sits at the edge of that disk, not at the edge of the hole. All of it is 55 million light-years away. At that distance, the whole structure spans about 42 microarcseconds on the sky. A microarcsecond is a millionth of a 60th of a 60th of a degree. To photograph something that small is roughly equivalent to reading the date stamped on a coin lying on a pavement in Los Angeles while standing at a window in Berlin. On the 10th of April 2019, a collaboration announced that they had done it. The instrument was not a telescope in the ordinary sense, because no telescope of the required size can be built. The resolving power of a radio dish depends on its diameter, and the diameter needed here is comparable to the diameter of the Earth. So the Event Horizon Telescope collaboration used the Earth. 8 radio observatories on 4 continents, including one at the South Pole, observed the same patch of sky at the same time, each recording the incoming radio waves along with an extremely precise timestamp generated by an atomic clock. Combining those recordings afterward produces the resolving power of a single dish as wide as the separation between the stations. The recordings were made in April 2017. The data volume was so large that transmitting it over any network would have taken longer than shipping it, so the hard drives were physically flown to correlation centers in Massachusetts and in Bonn. The drives from the South Pole could not be flown anywhere until the Antarctic winter ended and flights resumed, which is one of the reasons a photograph taken in 2017 was not released until 2019. Part of the delay in humanity's first image of a black hole was weather. What emerged was a ring of light, 42 microarcseconds across, give or take 3, surrounding a central region where the brightness dropped by a factor of more than 10. The size of the ring gave the mass directly, and the mass came out at 6.5 billion suns, in agreement with earlier estimates from the motion of stars and gas in the galaxy's core. 3 years later, on the 12th of May, 2022, the same collaboration released the image of the black hole at the center of our own galaxy. Sagittarius A star has a mass of about 4 million suns, which makes it roughly 1,600 times less massive than the one in Messier, 87. It is also about 2,000 times closer, at 27,000 light-years. Those two factors very nearly cancel, which is why the two objects appear almost the same size in our sky, and why one instrument was able to photograph both. That coincidence is not a physical law. It is luck, and it is the sort of luck that only becomes visible after someone has built the machine. Sagittarius A star was the harder of the two, despite being closer, and the reason is size. Gas orbits a 4 million solar mass black hole in minutes, not days. The source changes appreciably during the observation, which is the equivalent of photographing a running dog with a long exposure and then trying to reconstruct the dog. Producing an image required averaging over the variability rather than freezing it. There is a long history behind that particular target. In 1932, a young engineer at Bell Telephone Laboratories named Karl Jansky was investigating sources of static that interfered with transatlantic radio calls. He built a rotating antenna on a set of wheels taken from a Model T Ford, and he found 3 kinds of interference. 2 were thunderstorms, near and distant. The third repeated every 23 hours and 56 minutes, which is the length of a day measured against the stars rather than against the sun, and that timing meant the source was outside the solar system. He traced it to the constellation Sagittarius. Jansky had detected radio emission from the center of the galaxy more than half a century before anyone proposed that a black hole was responsible for it. The name itself came later. In 1982, an astronomer named Robert Brown working with observations of a compact radio source at the galactic center, needed a designation for it. He chose Sagittarius A star, with an asterisk, borrowing the notation used in atomic physics for an excited state, because the source was in his own description an exciting one. The name stuck, and it remains one of the very few objects in astronomy whose designation contains a small joke. The prediction of what these images would look like is much older than the images. In 1979, a French astrophysicist named Jean-Pierre Luminet calculated the appearance of a black hole surrounded by a disk of glowing gas, using a computer with less processing power than a modern kitchen appliance. The machine could not produce a printed image at the required quality, so Luminet took the numerical output and drew the picture himself, by hand, using India ink on negative paper, dot by dot. The result, a bright ring, a dark center, the far side of the disk lifted into view above and below the hole by the bending of light, is recognizably the same picture the collaboration released 4 decades later. In 2022, a team went back to the 2017 data on Messier 87 with a different approach. Instead of trying to resolve the second ring directly, which the array cannot do, they modeled and imaged simultaneously, fitting a physical description that included the sharp secondary ring and asking whether the data preferred it. The data did. The result was a reported extraction of the first of the nested images, the light that went around once before leaving. That measurement is a modeling result rather than a direct resolution, and the distinction matters. Resolving the second ring properly requires baselines longer than the diameter of the Earth, which means putting radio telescopes in orbit or on the far side of the Moon. Both have been proposed. Neither has been built. So the stack of older and older skies at the edge of every black hole remains, for now, a prediction supported by one careful inference. Here is what it would look like from inside the structure. You are on a trajectory that is very slightly outside the critical one, falling past the black hole rather than into it, and the sky begins to move in a way that no sky moves. The stars behind you slide forward, toward the black hole rather than away from it. As you approach the photon sphere, the entire universe compresses into a bright band that wraps around the dark circle ahead. Directly overhead, in that band, you find the same star twice. Then 4 times. Then, in a thin line of repeats marching inward, each copy dimmer and thinner than the last, each one showing the star as it was a fraction of a second earlier. The back of your own head is in there somewhere. In the innermost band you can distinguish, arriving as light that left you and went all the way around. The dark circle is not a hole in the sky. It is the one direction in which nothing arrives. None of this is inside the black hole. That is the point of putting it at number 10. Every photon in that structure is outside the horizon, and every one of them is eventually free to leave. What we have photographed is the outermost consequence of the object, the part of it that reaches furthest back into the ordinary universe, and it is already an infinite stack of images of a sky that no longer exists. The light in that ring is still outside, and still ours. The next entry on this list is the first one that touches the object itself. Number 9. The region where nothing can stand still. Every star rotates. The sun turns on its axis about once a month. Stars much more massive than the sun, the kind that end their lives as black holes, often rotate far faster than that. And when something rotating collapses, it does not lose its rotation. Angular momentum is conserved, the same way it is conserved when a figure skater pulls in their arms and speeds up. A star with a core 1,000,000 kilometers across, turning slowly, collapses into an object a few tens of kilometers across, turning very quickly indeed. So every black hole that exists in nature is spinning, and rotation changes the space around it in a way that has no equivalent in ordinary gravity. Around a spinning black hole there is a region, outside the event horizon, in which it is not possible to remain stationary. Not difficult. Not expensive. Not a matter of building a better engine. Impossible. Space in that region is being dragged around the hole faster than light can travel through it in the opposite direction, and so every object inside it, without exception, is carried around with the rotation. The region is called the ergosphere, from the Greek word for work, because work can be extracted from it. It is worth being precise about what is and is not being claimed, because this is one of the places where a correct statement sounds like an exaggeration. An object inside the ergosphere can still escape. It is outside the event horizon, and outward paths exist. A spacecraft in there could leave whenever it wanted. What it cannot do is hold position. A ship firing its engines at full thrust directly against the direction of rotation would still be swept around the hole, not because the engines are too weak, but because there is no path through that region that stays put. Standing still is not a thing that can be done there. The option has been removed from the geometry. The shape of the region is worth holding in mind because it is not a shell of uniform thickness. The outer boundary of the ergosphere is called the static limit, and it touches the event horizon exactly at the two poles, at the top and bottom of the rotation axis, where there is no dragging to speak of. Away from the poles it bulges outward, reaching its greatest extent at the equator, where for a rapidly spinning hole it sits at twice the horizon radius. The result is shaped roughly like a pumpkin with a smaller sphere inside it, and the space between the two surfaces is where standing still stops being available. The term ergosphere itself was introduced around 1971 by Remo Ruffini and John Wheeler, the same Wheeler who had popularized the phrase black hole a few years earlier, and who had a career-long gift for naming things in a way that made them stick. The mathematics that describes all of this arrived in 1963, and the story of how it arrived is worth telling properly. Einstein published the field equations of general relativity in 1915. Within weeks, a German physicist named Karl Schwarzschild, serving with the artillery on the Russian front, solved them for the case of a single spherical mass that is not rotating. He sent the solution to Einstein, who read it to the Prussian Academy on his behalf. Schwarzschild died 4 months later of an autoimmune disease contracted at the front at the age of 42. The rotating case then went unsolved for 47 years. It was not for lack of effort. The problem was known, it was obviously important, and it defeated everyone who tried it. The equations for a rotating mass are enormously more complicated than for a static one, because rotation breaks spherical symmetry and introduces a preferred axis, and the number of terms in the resulting expressions grows past the point where a human being can hold the calculation in view. By the late 1950s, the general feeling in the field was that the rotating solution might simply be beyond reach in closed form. In 1963, a 34-year-old New Zealand mathematician named Roy Kerr, working at the University of Texas, found it. He did not attack the general problem. He restricted attention to spacetimes with a particular algebraic property, which cut the problem down to a size a person could work through, and then he worked through it. The result was published as a paper of a little over 1 page in Physical Review Letters, titled with mathematical dryness, "Gravitational Field of a Spinning Mass," as an example of algebraically special metrics. Because everything in the universe rotates, and everything that collapses conserves its rotation, Kerr's solution, not Schwarzschild's, describes essentially every black hole that actually exists. Schwarzschild's is the teaching case. Scariest is the universe. Subramanian Chandrasekhar, who spent much of his own career on the theory of these objects and won a Nobel Prize for related work, later wrote that in his entire scientific life, the most shattering experience had been the realization that this exact solution of Einstein's equations, discovered by a New Zealand mathematician, provides the absolutely exact representation of untold numbers of massive black holes that populate the universe. One page of algebra, describing every one of them. The energy stored in that rotation is the reason the ergosphere is on this list, rather than in a footnote. A spinning black hole is not merely an object that happens to be turning. It is the most efficient energy store known to physics, and the energy is available. For a black hole rotating as fast as it is possible to rotate, up to 29% of its total mass energy is rotational, and can in principle be removed without anything ever crossing the horizon. Put that number beside the alternatives. Chemical burning converts something like 100 millionth of the mass involved into energy. Nuclear fusion, the process that runs the sun, converts about 0.7%. Matter falling onto a rotating black hole can convert up to about 42% of its rest mass into radiation before it disappears. And the spin itself is a reservoir holding nearly a third of the object's entire existence as extractable energy. The mechanism for getting it out was described by Roger Penrose in 1969, and it is elegant enough to state in a sentence. Send an object into the ergosphere. While it is in there, split it in two. Arrange the split so that one fragment falls through the horizon on a trajectory that has negative energy as measured by a distant observer, which is possible in there and nowhere else, and the other fragment flies back out. The escaping fragment carries away more energy than the whole object brought in. The black hole pays the difference out of its rotation and turns a little more slowly than it did before. There is a flaw beneath the process, and it was identified almost immediately. In 1970, Dimitrios Christodoulou showed that every black hole has an irreducible mass, a portion of its mass that no extraction scheme can ever remove. You can drain the rotation entirely, slowing the object until it no longer spins at all, and what remains is a black hole of that irreducible mass, from which nothing further can be taken. What makes this more than an accounting rule is a second property Christodoulou proved alongside it. The irreducible mass never decreases. Every process that takes energy out leaves that floor either unchanged or higher. It is possible to make a black hole give, but not to make it give back what it has already banked. That floor turns out to be the same quantity as the horizon area, expressed differently, which is a connection that will matter a great deal 2 entries from now. In 1970, nobody knew why a statement about extractable energy should be equivalent to a statement about surface area. It looked like a coincidence in the algebra. It was not. Nature does not appear to run the Penrose process with rocks. It runs a version of it with magnetic fields, and the result is visible across intergalactic distances. In 1977, Roger Blandford and Roman Znaczek showed that magnetic field lines threaded through the ergosphere by infalling gas are twisted by the dragging of space, and that the twisting drives an outward flow of energy in electromagnetic form. This is the leading explanation for astrophysical jets, the narrow beams that emerge from the centers of active galaxies and travel for enormous distances without spreading out. The jet from the black hole in Messier 87, the same object photographed in 2019, is about 5,000 light-years long. It was first noticed in 1918 by Heber Curtis at Lick Observatory, who described a curious straight ray connected with the nucleus, decades before anyone had a concept that could account for it. Set that length beside something familiar. The nearest star to the Sun is a little over 4 light-years away. The jet is more than 1,000 times longer than that distance, and it is powered by the rotation of a single object that no telescope can resolve, feeding on nothing but its own spin. Frame dragging, the effect underneath all of this, is not exclusive to black holes. It is a prediction for every rotating mass in the universe, including the one we are standing on, and it has been measured here. Gravity Probe B, launched in 2004 after more than 4 decades of development, carried 4 gyroscopes into polar orbit. To measure an effect that small, the gyroscopes had to be almost perfectly spherical, and they are among the most precisely manufactured objects ever made. Each is a fused quartz sphere about the size of a ping-pong ball, and the departure from a perfect sphere is so small that if the ball were scaled up to the size of the Earth, no mountain or valley on it would be more than about 2.5 meters from sea level. Over the course of the mission, the rotation of the Earth dragged the space around those gyroscopes and tilted their axes by about 37 milliarcseconds per year. That angle is roughly what a human hair would subtend at a distance of 10 kilometers. It took the entire apparatus, cooled to a fraction of a degree above absolute zero and shielded from the Earth's magnetic field, to detect a tilt of that size, produced by the whole planet. Around a spinning black hole, that same effect is not a slow drift measured over years. It is total. It is the dominant fact about the region. There is a consequence of this that is easy to state and difficult to picture. Drop an object toward a spinning black hole with no sideways motion at all, straight down along a line pointing directly at the center, released from rest. It will arrive at the horizon moving sideways. Nothing pushed it. There is no force acting on it in any conventional sense. The space it was falling through was rotating, and it went where the space went. The most dramatic demonstration of what black hole rotation contains came on the 14th of September 2015, when 2 detectors in Louisiana and Washington state registered a signal lasting about 0.2 of a second. 2 black holes, of roughly 36 and 29 times the mass of the Sun, had spiraled together and merged more than 1 billion light-years away. The final object came out at about 62 solar masses. 36 plus 29 is 65. 3 solar masses of material did not end up in the final black hole. It was radiated away as gravitational waves, as ripples in the shape of space itself, in about 0.2 of a second. To put that in a form that can be felt, for that fraction of a second, the power radiated by 2 invisible objects colliding exceeded the combined light output of every star in the observable universe by a factor of 10s. Nothing saw it. There was no flash. The energy went out as a change in the distances between things, and by the time it reached the Earth, the effect on a 4-kilometer instrument was a distortion smaller than the width of an atomic nucleus. The rotational energy that Penrose described a theoretical method for extracting in 1969 had, in that event, been released by 2 black holes with no help from anyone. There is one more property of the ergosphere worth naming, because it appears again in modern work. In 1971, Yakov Zeldovich showed that a rotating absorbing body will amplify waves that scatter off it, taking energy from the rotation and putting it into the wave. He worked it out for a spinning cylinder and pointed out that the same thing should happen for a spinning black hole. The effect is called superradiance, and it means that a wave sent toward a spinning black hole at the right frequency comes back stronger than it went in. Black holes are usually described as objects that take. In the right circumstances they give, and what they give away is their rotation. Zeldovich reportedly could not persuade his colleagues that the effect was real, and the argument was settled only when it was re-derived independently. The idea has had a long afterlife. If a spinning black hole is surrounded by anything that reflects waves back toward it, a shell of mirrors in the original thought experiment, or a cloud of very light particles in the modern version, then the amplified wave returns, is amplified again, returns again, and the process runs away. Searches for exactly this signature around known black holes are now used to place limits on the existence of hypothetical ultralight particles, which is a strange and pleasing use for a spinning object, a piece of particle physics apparatus built out of curved space and rotation, sitting in the middle of a galaxy that nobody had to construct. How fast do real black holes actually spin? The honest answer is that this is one of the harder measurements in astronomy, and the numbers are still moving. Spin has to be inferred indirectly, either from the shape of ion emission lines in the light from the innermost edge of an accretion disk, or from fitting the overall thermal spectrum, or from the details of a jet. The methods do not always agree with each other, and they carry model assumptions that are difficult to test. Estimates for the black hole in Messier 87 span a wide range depending on which approach is used. Estimates for Sagittarius A star are similarly unsettled, though the imaging results appear to favor a hole that is spinning appreciably and whose rotation axis points broadly toward us. This is not a small gap in the record. How fast a supermassive black hole spins is a direct record of how it grew. A hole that grew by swallowing gas from a steady disk, always arriving from the same direction, spins up toward the maximum. A hole that grew by merging with other holes arriving from random directions ends up spinning slowly, because the contributions partly cancel. The spin distribution is a history of galaxy assembly, written in a quantity that is very difficult to read. Everything in this entry can still be left behind. The ergosphere is outside the horizon. A ship in there is being carried around, but it can leave, and the energy extracted from it comes out and travels for thousands of light years as a jet or as a wave. The next entry on this list is about a surface that nothing leaves. Number 8. A surface that remembers everything that ever fell in. From the outside, nothing ever finishes falling into a black hole. This is not a figure of speech, and it is not a limitation of our instruments. It is what the geometry says. As an object approaches the horizon, the light it emits takes longer and longer to climb away from the object and reach a distant observer. The images arrive later and later, and further apart, and the object appears to slow down. Its light shifts toward the red end of the spectrum, then out of the visible band entirely, and it dims. And it never quite gets there. In the description used by an observer far away, an object falling into a black hole approaches the horizon and takes an infinite amount of time to reach it. From the point of view of the falling object, nothing of the kind happens. It crosses the horizon in a perfectly finite and rather short interval, and it notices nothing at the crossing. No barrier, no sensation, no marker of any kind. Both descriptions are correct. They are not competing accounts of the same events, one of which must be wrong. They are the same events described in two coordinate systems, and the disagreement between them is a property of the geometry rather than a paradox in it. For most of the 1960s, Soviet physicists called these objects frozen stars, precisely because of the exterior picture, and the name was accurate as far as it went. Yakov Zeldovich and Igor Novikov and their colleagues worked out much of the exterior behavior independently, and years before it was widely accepted in the West. There is a correction to make here, and it is the sort of correction that improves the story rather than deflating it, so it is worth making carefully. The frozen image is real, but it does not linger. As the infalling object approaches the horizon, its brightness does not merely dim gradually. It falls off exponentially, on a timescale set by how long light takes to cross the black hole. For a black hole of 10 times the mass of the Sun, that timescale is under 1/10 of a millisecond. For Sagittarius A star, at 4 million solar masses, it is a matter of tens of seconds. After a handful of those intervals, the light emitted by the infalling object has redshifted and dimmed past the point where any instrument that could be built would register a photon. So the frozen star is frozen and, almost immediately, invisible. The object hangs at the boundary forever in the mathematics and vanishes in under a millisecond in practice. This is exactly why the name frozen star fell out of use, and why the term black hole, which John Wheeler popularized in a lecture in 1967, replaced it. Nothing about a black hole looks frozen. It looks like an absence. What makes the exterior picture strange is not the freezing. It is what the surface turns out to have to hold. In 1972, a graduate student at Princeton named Jacob Bekenstein noticed a problem that nobody else appeared to be worried about. His supervisor, Wheeler, had made an offhand remark to him that whenever he put a hot cup of tea next to a cold one and let them come to the same temperature, he felt as though he had committed a crime, because the increase in entropy could never be undone. The universe would carry the consequences of that cup of tea forever. Unless, Wheeler said, you drop the evidence into a black hole. Bekenstein took the joke seriously. Drop a hot object into a black hole, and the entropy of the outside universe decreases. The second law of thermodynamics, the statement that the total entropy of a closed system never decreases, which is the single most robustly confirmed statement in all of physics, appears to be violated, and violated trivially, by anyone with a black hole and a cup of tea. His proposal was that the black hole has entropy of its own, and that this entropy is proportional to the area of its event horizon. Drop the tea in, and the horizon grows by exactly enough that the total entropy, inside plus outside, does not decrease. The second law survives, and it survives by making a statement about surface area. Stephen Hawking thought this was wrong. He had proven in 1971 that the total horizon area of a system of black holes can never decrease, a result now called the area theorem, and he regarded the resemblance to the second law as an analogy rather than an identity. Entropy comes with temperature, and a body with a temperature radiates, and a black hole by definition does not radiate. The idea appeared to be self-defeating. Then, in 1974, in the course of trying to demonstrate that it was self-defeating, Hawking found that black holes do radiate. That result gets its own treatment later on this list. What matters here is the formula it produced, because it is one of the very few equations in physics in which gravity, quantum mechanics, and thermodynamics all appear on the same line. The entropy of a black hole is 1/4 of the area of its horizon, measured in units of the Planck area. Consider what that means numerically, because the number is where the strangeness lives. A Planck area is about 10 to the power of -70 square meters. That is a small number in a way that ordinary comparisons cannot reach. It is to a square millimeter, roughly as a square millimeter is to a region far larger than the observable universe. The horizon of Sagittarius A star has an area of roughly 2 times 10 to the 21st square meters, a sphere about 25 million kilometers across, which is about 1/6 of the distance from the Earth to the Sun. Divide one by the other, apply the factor of 1/4, and the entropy of Sagittarius A star comes out at around 10 to the power of 90 in natural units. That number needs a comparison to be felt. Here is one. The overwhelming majority of the entropy in the ordinary universe, outside black holes, is carried by the photons of the cosmic microwave background, the leftover radiation from the early universe. There are something like 10 to the 88 of them within our horizon. So the surface of that one object, sitting in the middle of our own galaxy, carries roughly 100 times more entropy than every photon of the afterglow of the Big Bang in the entire observable universe, combined. And Sagittarius A star is not a large black hole. It is a modest one. The black hole in Messier 87, at 6.5 billion solar masses, has an entropy larger by another factor of more than 1 million, because entropy grows with the square of the mass. Now put that beside the other thing that is true of a black hole from the outside, and the tension becomes clear. Entropy counts possibilities. An entropy of 10 to the 90th means the object, considered as a physical system, distinguishes on the order of 10 to the 90th different internal states. And yet a black hole, viewed from outside, is the simplest object in physics. It has a mass, a spin, and an electric charge. That is the complete list. Two black holes with the same 3 numbers are identical in every measurable respect, no matter what they were made of, no matter how they formed, no matter what fell into them. One that swallowed a library, and one that swallowed an equal mass of hydrogen, are the same object. This was established as a series of theorems through the 1960s and 70s by Werner Israel, Brandon Carter, David Robinson, and others, and Wheeler summarized it in the phrase that black holes have no hair. Richard Feynman is said to have disliked the phrase on the grounds that it sounded obscene, and to have refused to use it. It stuck anyway. So the object has 3 numbers on the outside and 10 to the 90th distinguishable states in its accounting. Where are those states? The formula answers with an address, and the address is the surface. Not the volume. The capacity is 1 bit for every 4 Planck areas of horizon, which is a rule that no other physical system obeys. A hard drive holds more data if you make it thicker. A library holds more books if you add another floor. A black hole's capacity to hold distinctions is written on the surface, and adding depth adds nothing at all. Hold that phrase. It comes back at the end of this list, and when it comes back it will not be an accounting curiosity. The temperature that comes with that entropy is worth stating, because it runs in the direction nobody expects. A black hole's temperature is inversely proportional to its mass. Small holes are hot. Large holes are cold. Sagittarius A star sits at roughly 100th of a trillionth of a degree above absolute zero, colder than the cosmic microwave background, which fills all of space at about 2.7 degrees by 14 orders of magnitude. That comparison has a consequence that is easy to miss and worth stating plainly. Heat flows from hot to cold. The microwave background is warmer than every supermassive black hole in the universe, and warmer than every stellar mass black hole too. So none of them are currently evaporating. All of them are gaining mass, absorbing more from the background radiation than they emit, and they will go on doing so until the universe has expanded enough to cool that background below their own temperature. For the black hole at the center of our galaxy, that crossover is somewhere on the order of 100 billion years away. Everything that will be said later on this list about black holes evaporating describes a process that has not started yet, anywhere, for any of them. There is a broader rule hiding in the entropy formula, and it was extracted in the 1980s and 90s. If a black hole is the most entropy that can be packed into a region of a given size, and it is, because trying to exceed it collapses the region into a black hole, then there is a hard ceiling on how much information any region of space can hold, and that ceiling is set by the area of the region's boundary rather than by its volume. Raphael Bousso later sharpened this into a form that works in general curved spacetimes. It is a bound on reality itself, and it is nowhere near being reached by anything ordinary. The Earth stores something like 10 to the 67th times less information than its own surface area would in principle permit. The exterior picture was formalized in 1986 by Kip Thorne, Richard Price, and Douglas MacDonald in what is called the membrane paradigm. Their claim is a practical one. For every purpose that an observer outside the horizon could ever care about, a black hole behaves exactly like a physical membrane sitting just above it, a thin surface with an electrical conductivity, a viscosity, a temperature, and a specific electrical resistance of 377 ohms. That last number is not arbitrary, and it is not chosen to be memorable. 377 ohms is the impedance of free space, the resistance that empty vacuum presents to an electromagnetic wave passing through it. The horizon terminates field lines in exactly the way a surface of that resistance would. Engineers who work on the electrodynamics of jets and accretion flows use the membrane description because it works, not because it is a helpful picture. The equations they solve are the equations of a resistive surface. Leonard Susskind pushed this considerably further in 1993 with a proposal he called black hole complementarity, and it is the most philosophically demanding idea in this entry. The two descriptions, one in which everything that ever fell in is smeared across a hot membrane just above the horizon and will eventually be radiated back out, and one in which everything sailed through an unremarkable boundary and is on its way inward, are, Susskind argued, both complete and both correct. There is no fact of the matter that decides between them. And no contradiction arises, because no observer can ever check both. An observer who stays outside sees the membrane story and can never see the interior. An observer who falls in sees the interior story and can never report back. The two accounts are never available to the same person, and so the universe is never caught contradicting itself. That is either a deep insight about the nature of physical description or a very sophisticated way of not answering the question, and the field has argued about which for 30 years. The argument comes to a head 2 entries from now. Meanwhile, the area theorem, the result Hawking proved in 1971, that horizon area never decreases, sat for 50 years as a piece of pure mathematics about a kind of object nobody had ever directly observed. In 2021, a group tested it. They used the first gravitational wave detection, the merger recorded in 2015. The signal from such an event has 2 useful halves. The long in spiral, before the collision, encodes the masses and spins of the 2 original black holes, and from those you can calculate the area of each horizon. The ring down afterward, as the merged object settles, encodes the mass and spin of the final black hole, and from those you can calculate its horizon area. The 2 calculations use different parts of the signal and different physics. The final area came out larger than the sum of the 2 initial areas, at 95% confidence. Consider what that sentence contains. A law about heat engines, formulated in the 1850s by people studying steam, restated in 1971 as a theorem about the geometry of space-time, was tested against the collision of 2 black holes more than 1 billion light-years away, using an instrument that measures distance changes smaller than the width of an atomic nucleus, and it held. Here is the moment inside all of this that is worth sitting with. Picture a single photon, emitted by something 1 meter above the horizon of Sagittarius A star, aimed straight out. It leaves at the speed of light, and it climbs. The climb costs it energy, not speed, which never changes, but wavelength, which stretches. Green becomes red. Red becomes infrared, then microwave, then radio. The stretching continues the whole way out, because the photon is still climbing, still working against a geometry that goes on for millions of kilometers. By the time it has cleared the region where the effect matters, its wavelength is longer than the black hole is wide. By the time it reaches the outer galaxy, it is a ripple in the electromagnetic field, so faint and so stretched that no antenna could distinguish it from nothing at all. It is still traveling. It will keep traveling. And it carries, in its extraordinary redness, the only information anything outside will ever receive about the last meter of its source's existence. Whatever record that surface holds includes, in principle, every star and every cloud and every planet the black hole has ever swallowed, written at a density of 1 bit per 4 Planck areas, across a sphere the width of a sixth of the Earth's orbit. All of which assumes that there is somewhere for that information to have gone, and that the doorway it went through is a doorway. The next entry on this list is an argument that it may not be. Number 7. The wall of fire at the doorway. In 1907, sitting at a desk in the patent office in Bern, Albert Einstein had a thought that he later described as the happiest of his life. A person falling freely, he realized, does not feel their own weight. Drop someone off a roof, and for the duration of the fall, gravity is undetectable to them. Every object around them falls at the same rate, so nothing moves relative to anything else, and no experiment performed inside the falling frame can reveal that gravity is present at all. That observation grew into the equivalence principle, and the equivalence principle grew into general relativity. It is the load-bearing assumption of the entire theory. Gravity is not a force acting on objects moving through space. It is the shape of space, and free fall is what motion looks like when nothing is interfering. Apply that principle to a black hole, and you get a specific, checkable prediction. The event horizon of a large black hole is not a place where anything local is extreme. Curvature there is gentle. Tidal effects are mild. Nothing about the geometry at that surface is any more violent than the geometry in your living room. So an observer falling through the horizon should notice nothing whatsoever. No barrier, no jolt, no flash, no signal of any kind. They cross a boundary that is unmarked, and the only way they could know is by doing arithmetic. Physicists have a name for this prediction. They call it no drama. In July of 2012, 4 physicists working at the Kavli Institute for Theoretical Physics in Santa Barbara published a paper arguing that no drama, quantum mechanics, and the existence of a smooth interior cannot all three be true at once. Something has to break. And after working through every way they could find to avoid the conclusion, the option they found hardest to eliminate was that an observer falling into an old black hole does not pass through the horizon at all. Instead, on arrival, they meet a sheet of extremely energetic quanta and are destroyed instantly. The authors were Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully. The name that stuck to their proposal is the firewall. The argument takes some care to lay out, but every step of it uses physics that is well established, and that is precisely what makes it hard to dismiss. There is no quantum gravity in it. There is no string theory in it. It uses quantum mechanics, general relativity, and thermodynamics, each in the regime where each has been tested and each is trusted, and it shows that in one specific circumstance, they cannot all be right. Start with Hawking radiation, which arrives properly at number 4, but needs a sentence here. Near the horizon, the quantum vacuum produces pairs of particles. One member of each pair falls in, the other escapes and travels away as radiation. The 2 members of a pair are entangled, correlated in the particular quantum way that means neither has a definite state on its own, and only the pair together is fully described. That entanglement is not incidental. It is what makes the horizon smooth. An empty, ordinary, featureless vacuum at the horizon just is a state in which those pairs are correlated across it. Break the correlation, and you do not get a smooth vacuum with a small defect. You get a region full of high-energy particles, because in quantum field theory, the absence of the expected correlations is what energy looks like. It is worth slowing down on that point, because it is the least intuitive step, and everything else rests on it. In quantum field theory, the vacuum is not nothing. It is a state with structure, and one of its most important structural features is that measurements made at neighboring points are correlated. Those correlations are what make the vacuum smooth. If you were to reach into empty space and sever the correlations across an imaginary surface, leaving the two sides intact but no longer related to each other, the result would not be a slightly duller vacuum. It would be a sheet of energy sitting where the surface was. Correlation is not decoration in this theory. It is what emptiness is made of. There is an established and closely related result that makes the same point from another direction. In 1976, William Unruh showed that an observer accelerating through empty space detects a thermal bath of particles at a temperature proportional to the acceleration, while an observer floating alongside them in free fall detects nothing at all. Same region of space, two observers, one sees warmth and one sees vacuum. The disagreement is not a failure of one of the instruments. It is a genuine feature of quantum field theory in a curved or accelerated setting, and it is the mechanism underneath Hawking radiation. An observer hovering above a black hole is accelerating, permanently, just to stay put, and what they detect is the heat that goes with it. So the smoothness of the horizon is not a claim about the horizon looking uneventful. It is a claim about a specific pattern of correlations existing across it. Break the pattern, and the observer who falls through does not find a subtle absence. They find a wall. So far, so consistent. Now add the requirement that black hole evaporation is reversible in the way quantum mechanics demands. Quantum mechanics is unitary. Information is never destroyed. It can be scrambled beyond any practical hope of reconstruction, but the underlying process always preserves it in principle. If black hole evaporation is unitary, then the radiation coming out has to carry away the information about what fell in. And Don Page worked out in the early 1990s what that requires the radiation to look like as a function of time. Early on, each escaping particle is essentially random, and the entanglement between the radiation and the hole grows. But past a certain point, when the black hole has radiated away about half its entropy, a moment now called the Page time, the pattern must reverse. From then on, every newly escaping particle has to be entangled with the radiation that came out earlier, so that the total emerging record becomes gradually more and more complete. The curve of entanglement entropy rises and then comes back down. It is called the Page curve, and if evaporation is unitary, the curve is not optional. Now put the two requirements side by side. For an old black hole, past its Page time, a newly escaping Hawking particle has to be entangled with the early radiation, or unitarity fails. And it has to be entangled with its infalling partner, or the horizon is not smooth. It cannot do both. This is not a matter of interpretation, or of how hard the calculation is. Entanglement is monogamous. A quantum system that is maximally entangled with one thing cannot also be maximally entangled with another. That is a theorem, proven from the structure of quantum mechanics itself, and there is no known way around it. So one of three assumptions has to go. Either information really is destroyed inside black holes, and quantum mechanics does not apply to them, which almost nobody is willing to accept because unitarity is not a detail of the theory, but its skeleton. Or the low-energy physics that we trust in every other setting fails far outside the horizon, in a region where nothing is extreme and the theory has no business failing, which is nearly as unpalatable. Or the entanglement across the horizon is broken, and since severing it costs energy, the horizon of an old black hole is a sheet of high-energy quanta. A wall, not a doorway. There is a further piece of the picture that explains why the page time is the moment things go wrong, rather than some other point in the process. In 2007, Patrick Hayden and John Preskill worked out how quickly a black hole scrambles information that falls into it, how long it takes for a message thrown in to become spread across the object's degrees of freedom so thoroughly that no local measurement can recover it. The answer was that black holes are the fastest scramblers permitted by physics. Nothing in nature mixes information more quickly. Their result had a consequence that sounds like science fiction and is a straightforward calculation. If a black hole is already past its page time, then the radiation that has escaped is, in the technical sense, a nearly complete record of everything the hole contains. Throw a new object in, wait only for the scrambling time, and the information about that object comes back out in the radiation almost immediately, provided you have collected and stored every photon of the earlier radiation and can perform an arbitrarily complicated computation on it. The black hole, past the halfway point, behaves like a mirror with a delay. That is the setting the firewall argument requires. Not a hypothetical. A consequence of taking unitarity seriously. And it is the reason the contradiction appears only for old holes. It takes half the object's lifetime for the outgoing radiation to become a record complete enough for the monogamy problem to bite. What happened next in the field is worth describing because it says something about how physics behaves when it is genuinely confused. The paper was disruptive in a specific way. Everybody involved wanted it to be wrong, and nobody could show that it was. Leonard Susskind, whose complementarity proposal of 1993 was the framework the argument was designed to stress test, described the situation as a crisis. Papers appeared at a rate of several a week for the better part of a year. Conferences were reorganized around it. And there is a detail here that deserves to be stated plainly, because it changes the character of the whole episode. Joseph Polchinski, one of the four authors, had spent much of his career building the theoretical framework that the argument threatened. He was not an outsider attacking a structure he disliked. He was one of its architects, running an audit of his own building and reporting that it did not pass. That is not a common thing, and it is one of the more admirable things this subject contains. The responses have been numerous and inventive. In 2013, Juan Maldacena and Susskind proposed that entangled particles are connected by microscopic wormholes, that the bridge between two regions of spacetime, first described by Einstein and Nathan Rosen in 1935, is the same thing as the quantum entanglement described by Einstein, Boris Podolsky, and Rosen in the same year. The slogan is that Einstein-Rosen equals Einstein-Podolsky-Rosen. If it is right, then the late Hawking particle can be entangled with the early radiation and with an interior partner without violating monogamy, because those would not be two different things. They would be the same thing, connected through a geometry, seen from two directions. Others took a different route and argued that the interior is not a separate region at all, but something reconstructed from the radiation itself. That line of thinking matured, between 2019 and 2020, into a set of calculations that finally produced the page curve from gravity rather than assuming it, and those calculations are the reason this list ends where it does. They are the subject of number 1. A third line of response questioned whether the infalling observer could ever verify the contradiction in practice. To catch the black hole violating monogamy, someone would have to collect essentially all the radiation emitted over the first half of the object's life, perform a computation on it of almost unimaginable complexity, extract the result, and then dive in and compare it against what they find inside, all before reaching the singularity. Daniel Harlow and Patrick Hayden showed in 2013 that the required computation appears to be hard in a precise, technical sense, quite possibly taking longer than the black hole's remaining lifetime. That does not make the contradiction go away. It suggests that nature may protect itself by making the check unaffordable, which is either a deep principle or a very convenient accident, and there is not yet any agreement on which. Polchinski died in 2018, at the age of 63, with the question he had sharpened still open. The paper that carries his name on this problem has been cited well over 1,000 times, and the situation it describes has not been resolved so much as reorganized. Most of the field now believes the first horn, the destruction of information, has been eliminated, which leaves the other two, and no consensus on either. It is worth being clear about what the firewall proposal actually claims is inside a black hole, because it belongs on this list for a specific reason. It does not claim there is something new and dangerous in the interior. It claims there may be no interior. Under the firewall picture, the horizon is not a surface you pass through on your way somewhere. It is the end of space-time, a boundary of the manifold, where the description stops rather than continues. Everything this list has said about the region behind that surface, and everything it is about to say, would refer to a place that does not exist. The title the four authors chose is worth noting, because it has been widely misreported. The paper is called Black Holes, Complementarity or Firewalls, with a question mark at the end. They were not announcing that a wall exists. They were pointing out that a set of assumptions everyone held simultaneously could not all be held, and inviting the field to say which one it wished to give up. The question mark was the whole point, and it is the part that tends to fall off in retelling. It is also worth trying to picture what each of the three options would mean for someone actually making the descent, because the three are not equally strange in the same way. Under the first option, information is destroyed. The observer falls through an unremarkable horizon, reaches whatever is inside, and everything they were is genuinely gone from the universe, not scrambled, not hidden, gone. The descent feels like nothing. The cost is paid somewhere else entirely, in the foundations of quantum mechanics, and the price is that the theory which underpins every other branch of physics has an exception. Under the second option, the observer never gets near the horizon in the state they expect, because the ordinary description of space has already stopped applying much further out, in a region where curvature is mild and nothing looks unusual. The failure is invisible, and it is enormous. It would mean that the theory we use to describe everything from semiconductors to starlight quietly stops being valid in an ordinary-looking region for reasons that have to do with radiation that departed long ago. Under the third, the descent proceeds exactly as expected until the last instant, and then ends at the boundary, at energies with no upper bound in sight. The observer is not crushed by gravity. Gravity there is gentle. They are destroyed by the vacuum, failing to be a vacuum. Every one of those is a large claim. That is what a trilemma is, a place where all the exits are expensive. That is the argument. Here is what is not true about it. The firewall, if it exists at all, is a feature of old black holes, specifically of black holes past their page time. For a black hole of one solar mass, the page time is on the order of 10 to the 67th years. The universe is about 14 billion years old, which is 10 to the 10th. So every black hole in the observable universe is, by this standard, newborn. Not one of them is remotely close to the age at which the argument bites. Whatever is at the horizon of the object in Messier 87, it is not a firewall, because there has not been time. There is also a version of the argument's own history that is worth knowing. Susskind, Laurus Thorlasius and John Uglam's 1993 complementarity paper had already contained the seed of the problem. It argued explicitly that no single observer could ever catch the contradiction between the interior and exterior stories. The firewall paper was, in effect, a very careful attempt to catch it anyway, to construct the observer who could check both and see what broke. Stephen Hawking's response, in a short note in 2014, was more radical than the firewall itself. He suggested that true event horizons never form at all, that black holes possess only apparent horizons, temporary surfaces that trap light for a long time and eventually release it, and that the absence of a true horizon dissolves the problem by removing the surface the argument is about. Most of the field found this harder to accept than the wall. And there is one more property of the firewall argument worth stating, because it is the reason it has not gone away. The energies involved are set by the horizon's own scale, and for a stellar mass black hole, those energies are far beyond anything an accelerator will ever reach. There is no experiment. There is no observation. This is a dispute that will be settled, if it is settled, by someone finding an error in a chain of reasoning, or by someone constructing a consistent account that does not require the wall. That is an unusual position for physics to be in, and it is worth sitting with for a moment. The equivalence principle is the safest, most beautiful, most thoroughly confirmed assumption in the entire theory of gravity. It says that falling is just falling, that there is no experiment you can do in a sealed room that distinguishes a fall toward a black hole from floating in empty space. 4 people took the field's own best ideas seriously, followed them to the end, and found that at exactly one kind of surface, that assumption may fail. Not because anything is wrong with the surface, because of an accounting problem involving particles that have already left. Suppose you do get through, though. Suppose the wall is not there, and the horizon is what the equivalence principle says it is, an unmarked boundary that you cross without noticing. What waits on the other side is a space that does not behave like space. Number 6, an inside larger than any outside. We are halfway down this list, and it is worth taking a moment to see what has already changed. We began outside, with light in orbit, a structure that has been photographed, containing an infinite stack of older and older pictures of the sky. We moved to a region where standing still has been removed from the list of available options, and where nearly a third of an object's entire mass sits in its rotation, waiting to be taken. Then to a surface that holds more entropy than every photon of the afterglow of the Big Bang, and that stores its accounting on its skin rather than in its interior. And then to an argument, made by 4 people who did not want it to be true, that the surface may not be a doorway at all. Every one of those has been about the boundary or the outside. From here on, this list is about the interior, and the first thing to understand about the interior is that it is not a room. Inside the event horizon of a non-rotating black hole, the radial direction stops behaving like a direction and starts behaving like a time. That sentence is usually delivered as a poetic flourish, and it is not one. It is a statement about the mathematics, and it can be stated precisely. In the geometry outside the horizon, the coordinate we call distance from the center behaves the way distances behave. You can move toward larger values or smaller ones, freely, in either direction, and how fast you do so is up to you. The coordinate we call time behaves the way time behaves. you move forward through it, at a rate you do not choose and cannot reverse. Inside the horizon, those two coordinates swap roles. The radial coordinate acquires the properties that time had. Decreasing radius becomes a direction in time, and moving towards smaller radius becomes as unavoidable as moving toward tomorrow. And meanwhile, the coordinate that was time outside becomes a spatial direction, one you can move along in any other direction, and which has effectively unlimited extent. This has a consequence that resolves one of the most common misunderstandings about black holes. People sometimes ask why a sufficiently powerful rocket cannot escape once it is inside. The answer is not that the pull is too strong. There is no direction to point the rocket. Escaping would require moving toward larger radius, and larger radius is in the past. A rocket cannot help you with that. No amount of thrust makes yesterday reachable. It also means that the shape of the interior is not what the word interior suggests. The inside of a black hole is not a ball of space with the horizon as its skin and something at the center. In the geometry, it is closer to a tube, a long tunnel whose circumference is fixed by the horizon area and whose length runs in the direction of time. And because the length runs in time, the tube is not a static object. It gets longer. It is worth being careful about where the singularity sits in this picture, because the tube image makes it clear in a way the ball image never does. If the interior is a tunnel whose length runs forward in time, then the singularity is not at the center of anything. It is the far end of the tunnel. It is not a place in the middle that you fall toward. It is the moment the tunnel stops. Everything inside reaches it, not because everything is being pulled to the same location, but because everything is moving forward through time, and the geometry has an end. There is a second consequence of the swap that is easy to state and hard to accept. Two black holes that formed in completely different ways, from completely different material, have identical interiors in this description, provided their mass, spin, and charge agree. Not similar. Identical. A black hole that formed from the collapse of a blue supergiant and one that formed from the merger of two neutron stars arriving at the same three numbers are the same object in every respect anything can measure. The history is not stored in the shape. Where the history went is the question this entire list circles. Which leads to a question that sounds simple and is not how much room is in there. In ordinary space, this is a trivial question. Draw a surface, measure the volume it encloses, done. In curved spacetime, it is not trivial at all, and the reason is worth understanding because it applies to everything else on this list. To speak of the volume inside something at a given moment, you have to decide what moment means across an extended region. You have to slice the four-dimensional geometry into a three-dimensional snapshot. In ordinary circumstances, every reasonable way of slicing gives essentially the same answer, and the ambiguity does not matter. Inside a black hole, the different slicings give wildly different answers. There is no natural choice, and the differences are not small corrections. They are factors of enormous size. For most of the history of this subject, the question was simply set aside. The standard textbook position was that asking for the volume inside a black hole was a badly posed question, that the answer depended entirely on an arbitrary choice, and that nothing physical could turn on it. That is a defensible position, and it has the advantage of being safe. It also has the disadvantage of leaving a very large object undescribed. In 2014, two physicists, Marios Christodoulou and Carlo Rovelli, decided to ask the question properly rather than avoid it. Their approach was to take a definition of interior volume that works perfectly well in flat space and see what it gives inside a horizon. The definition is this: of all the possible surfaces that fill in a given boundary, take the one with the largest volume and call that the volume inside. In ordinary space, this returns exactly what you expect. Apply it to a sphere in your kitchen and you get the volume of the sphere. Apply it inside a black hole and two things happen, and both of them are strange. The first is that the answer is not fixed. It grows. The interior volume of a black hole, by this definition, increases steadily with the time elapsed since the object formed, while the horizon area, the thing an outside observer can measure, stays exactly the same. A black hole that has not swallowed anything for 10 billion years has precisely the surface it always had, and an interior that has been getting larger the entire time, without anything going in and without anything changing outside. The second is the size. Their own summary of the result is that a black hole with a horizon radius of 1 million kilometers can contain a volume equivalent to 1 million solar systems. Set that against the object at the center of our galaxy. Sagittarius A star has a horizon roughly 25 million kilometers across, about 1/6 of the distance from the Earth to the Sun. As an outside object, it is not enormous. You could fit it inside the orbit of Mercury with a wide margin. And it has been sitting there, by most estimates, for something on the order of 10 billion years, which means the interior volume by this measure exceeds anything the exterior dimensions would lead you to guess by a factor with no useful name. The obvious objection is that this must be an artifact, that any sufficiently perverse choice of coordinates can be made to produce a large number, and that the result says more about the definition than about the black hole. It is a fair objection, and the answer to it is the reason the result is taken seriously. The same definition, applied to anything ordinary, gives the ordinary answer. Apply it to the Earth, and you get the volume of the Earth. Apply it to a sphere drawn in empty space, and you get the volume of that sphere. Apply it to a neutron star, the densest object in the universe that still has a surface, and you get the volume of a neutron star. The definition only produces something strange where the geometry is strange, and inside a horizon, the geometry is a lengthening tube rather than a fixed ball. The volume grows because the tube grows, and the tube grows because its length is measured in a direction that is running forward, whether anyone is watching or not. There is a way to make the growth feel less like an abstraction. Think of the interior not as a container that is being filled, but as a corridor that is being extended at the far end. The circumference of the corridor is fixed. It is set by the horizon area, and the horizon area only changes when something falls in. But the corridor keeps being built in the only direction available to it, which is forward. A snapshot taken today, sliced in the way that maximizes the volume, catches more corridor than a snapshot taken 1 billion years ago. Nothing was added. The geometry simply has more of itself to show because more time has passed. That is why the growth does not violate anything. No mass appeared. No energy was created. The horizon area, which is what the outside world can measure and what the thermodynamics depends on, has not moved. What grew was the amount of geometry available to be counted, and geometry is not a substance. The result appeared in Physical Review D in 2015 and generated a substantial follow-up literature, including work on how the volume behaves for very old black holes and whether it can be connected to entropy in any useful way. Nobody has produced a clean answer to that second question. But the discussion has had a useful side effect. It has made the field considerably more careful about the phrase "inside a black hole," which turns out to smuggle in an assumption about simultaneity that the geometry does not support. That is the deepest oddity in this entry, and it deserves stating on its own. There is no moment at which the interior of a black hole exists all at once. A snapshot volume is a construction, chosen by whoever is doing the constructing. Asking how much space is in there is a little like asking how long a piece of music is in meters. The question can be given an answer, and the answer can even be meaningful, but only after somebody decides on a translation, and different translations give different numbers by enormous factors. There is an older idea in the same territory, and it has one of the better names in physics. In 1964, John Wheeler described a class of spacetimes in which an arbitrarily large region of space is connected to the outside universe through an arbitrarily small opening. He called them bags of gold. General relativity permits them. Nothing in the theory ties the volume enclosed by a surface to the area of that surface. That connection is a fact about flat space, and flat space is a special case rather than a rule. We are so accustomed to the flat space version that the alternative sounds like a trick. It is not a trick. It is the general case, and our intuition is the special one. Wheeler's phrase came out of a discussion about whether the geometry of space could conceal an arbitrary amount of material behind a small window, and the answer he arrived at was yes, in principle, with no bound. The construction requires the region behind the window to be curved in a particular way, and nothing forbids that curvature. It has been used since as a test case. Any proposed principle claiming that the information content of a region is limited by its boundary has to explain what happens in a bag of gold, where the interior can be made as large as anyone likes, while the boundary stays the size of a dinner plate. That tension has never been fully resolved, and it is not a marginal technical issue. It sits directly beneath the question this list ends on. Now put this beside the entry 2 places up the list, because the collision between them is the reason this item sits at number 6 rather than lower. From the outside, a black hole's capacity to hold information is set by the area of its horizon, and that area is fixed. It does not change unless something falls in. From the inside, the volume available grows without any upper limit, for as long as the object exists. Both are descriptions of the same object. So either the growing interior contains no additional information, in which case a great deal of room is doing nothing at all, or the information in that interior is somehow encoded on a surface that is not getting any bigger. The second option is the holographic claim, and it is where this list ends. This is not merely a philosophical tension. It is one of the specific technical reasons the information paradox is hard. If a black hole's interior grows without bound while its surface stays fixed, and if the surface is where the accounting happens, then the relationship between the two descriptions cannot be a simple one. One more clarification before we go on, because it matters for the 2 entries that follow. Everything in this entry describes a black hole that is not rotating, and no black hole in nature is not rotating. In the rotating case, the swap between space and time still happens when you cross the outer horizon, but it does not last. There is a second surface further in, and on crossing that one, the coordinates swap back. Radius becomes an ordinary direction again. Time becomes time again. The corridor opens back out into something that behaves, locally, like a room. That is the geometry of a rotating black hole as the equations describe it, and it is the reason the next 2 entries exist. The unavoidable, forward-only stretch is a stretch, not a permanent condition. Something is on the other side of it. Whether anything survives the crossing to find out is the subject of number 4, and what the equations say is waiting there is the subject of number 3. It is also why the phrase, "the interior of a black hole," is doing more work than it looks. There are at least 2 interiors, with different geometries, separated by a surface where the character of space and time reverses for the second time. What remains genuinely unsettled here is worth naming. Whether the maximal slice definition is the physically meaningful one is debated, and other reasonable definitions give other growth laws. Whether the growing interior can actually hold more information than the horizon permits, or whether it is large but empty of distinctions, is not resolved. And there is a subtlety that must not be skipped. The growth of the interior is a statement about a family of ways of slicing the geometry, not about anything an infalling observer would experience. An observer inside does not find themselves in an expanding cathedral. They reach the end in a short, finite, and entirely unforgiving interval, which is the next entry and the shortest one on the clock. Every one of those growing interiors ends the same way, at the same moment, for everything inside it. Number 5. A place you cannot steer away from. The singularity is the part of a black hole that everyone has heard of, and almost nobody has heard described correctly. The standard description is a point at the center where density becomes infinite and the laws of physics break down. Inside a black hole that is not rotating, it is not a point, it is not at the center, and calling it a place at all is the main error. The infinite density is not what the theorems establish. And the phrase, "the laws of physics break down," while roughly right in spirit, hides something more interesting than it reveals. Start with the geometry, because the previous entry set it up. Inside the horizon, the radial coordinate is time-like. Decreasing radius is a direction in time, not in space. So the singularity, the place where radius reaches zero, is not a location that could in principle be avoided by steering away from it. It lies in the future of everything inside the horizon. Every path, for every object, at every speed, in every direction, arrives there. It is not somewhere you fall toward. It is a moment that arrives. That reframing does more work than any other single sentence in this subject. It explains why nothing escapes. Escape would require a direction, and the direction is time. It explains why the interior cannot be surveyed and reported on. There is no vantage point that stands outside the event and looks at it. And it explains why the question, "What does the singularity look like?" has no good answer. You do not approach it and see it in front of you. It is not in front of you. It is later. Now the theorem. In January of 1965, Roger Penrose published a paper of about 3 pages in Physical Review Letters. Its central innovation was a concept he called a trapped surface, a closed two-dimensional surface with the property that light emitted from it converges in both directions. Send a flash of light outward from an ordinary sphere, and the wavefront expands. Send it inward, and it contracts. On a trapped surface, both wavefronts contract. Even the outgoing light is being pulled inward faster than it can move away. Penrose then proved that once a trapped surface forms, given some reasonable assumptions about energy and about causality, the space-time must be geodesically incomplete. There must exist paths through it that simply end after a finite interval, paths that a light ray or an object could follow, which stop with nothing beyond. That is the actual content of the singularity theorem, and it is both weaker and more unsettling than the popular version. It does not say the density becomes infinite. It does not say what happens to whatever was traveling along the terminated path. It says that the description ends. General relativity does not so much break down at the singularity as announce, in a formal and rigorous way, the boundary of its own jurisdiction. The word incompleteness deserves a moment, because it is doing something unusual. In ordinary physics, when a description fails, it fails by producing a quantity that grows without bound, a temperature that runs to infinity, a density that does the same, and everyone understands that the theory has been pushed past its range. Geodesic incompleteness is a different kind of failure. It is a statement about paths. Take the world line of a falling object, follow it forward, and at some finite point there is no further to go. Not blocked. Not obstructed. The manifold does not continue. The nearest ordinary comparison is a map that has been torn. You can walk along a road on the map, and then the paper ends, and the question of what is past the tear is not a question the map can answer, not because the map says nothing is there, but because the map has stopped. The singularity theorems say that any spacetime containing a trapped surface has a tear in it somewhere, and they say so without needing to know what the paper is made of. Penrose and Hawking then extended the result in a direction that made it considerably larger. If you take the expanding universe and run it backward, the conditions of the theorem are satisfied there too. The same mathematics that says a collapsing star must produce an incomplete path says the universe must have begun on one. Whatever else is true of the beginning, general relativity ends its own account of it, in the same way it ends its account of the inside of a black hole, mid-sentence. To appreciate why this mattered so much at the time, you need to know what people believed before it. The Schwarzschild solution had contained a singularity since 1916, and for decades, the consensus was that this was an artifact of perfect symmetry. Schwarzschild's solution describes an exactly spherical mass collapsing exactly symmetrically toward an exact center, and real stars are not exact. Real collapse is lumpy, uneven, and rotating. The expectation, held by serious people, including for a while Einstein himself, was that a realistic collapse would produce infalling material that missed the center, swirled past it, and bounced back out. The singularity was a bookkeeping artifact of an idealization. Penrose's theorem removed that hope without assuming any symmetry at all. That is the reason it is a landmark. It says nothing about what the collapsing star looks like. It requires only that a trapped surface forms somewhere, which happens for any sufficiently compact concentration of mass, regardless of its shape. Once that happens, incompleteness follows. The trapped surface also has the useful property of being detectable in principle rather than only in idealization. It does not require you to know where the center is or whether there is a center. It does not require the collapse to be symmetric or the matter to be of any particular kind. You only have to establish that somewhere in the mess of an imploding stellar core there exists one closed surface from which even outgoing light is converging. Once that condition is met anywhere, the conclusion follows for the whole space-time. That is why the theorem survived the objection that had defeated every earlier argument. It does not care what the star looked like on the way down. He received the Nobel Prize in Physics for it in 2020, 55 years later, and 2 years after the death of Stephen Hawking, with whom he had extended the theorem from collapsing stars to the universe as a whole. Penrose has said the idea of the trapped surface arrived while he was mid-conversation, crossing a side street in London, and that the thought was interrupted by the traffic and lost. He noticed later in the day that he was in an unexplained good mood, worked backward through everything he had thought about since morning, and recovered it. There is a way out of the theorem, and it is worth naming precisely, because it is where every serious attempt to avoid a singularity begins. The proof requires an energy condition, a technical assumption to the effect that energy density, measured by any observer, is not negative. Ordinary matter satisfies it comfortably. Stars, gas, dust, radiation, all of it. But quantum fields do not always satisfy it. There are well-understood configurations in which the energy density in a region is measurably below the vacuum value, which is to say negative, and the effect has been confirmed in the laboratory in the form of the attraction between two closely spaced uncharged plates. So the theorem does not say singularities exist. It says that if energy behaves classically all the way down, they do. Every proposal on this list that removes the singularity works by pointing at that assumption and arguing that it fails in the one place where it matters most. Now the numbers, because there are two, and they are the most concrete facts on this entire list. The first is that once you cross the horizon, the time you have left is bounded, and the bound depends only on the mass of the black hole. The maximum possible interval of experienced time between crossing the horizon of a non-rotating black hole and reaching the singularity is a little over 15 microseconds per solar mass. Run that for real objects. For a stellar mass black hole of 10 solar masses, the maximum is about 1/6 of a millisecond, less time than it takes a nerve signal to travel a centimeter. For Sagittarius A star, at 4.3 million solar masses, it is about 66 seconds. For the black hole in Messier 87, at 6.5 billion solar masses, it is roughly 28 hours. The larger the black hole, the longer the interior lasts. This is the reverse of the usual intuition, in which bigger means more dangerous, and it follows directly from the fact that the horizon of a large hole is further from the center. The second number is not really a number. It is a theorem that reads like a moral instruction, and it is one of the strangest true things in physics. That maximum interval is achieved by falling freely and doing nothing. Any use of engines shortens it. If you cross the horizon of Sagittarius A star and then fire your thrusters to slow your descent, to buy time, to fight, to delay the arrival, you will reach the singularity sooner than if you had done nothing at all. Not marginally sooner. Substantially. The reason is that inside the horizon, the singularity is in the future, and acceleration is what shortens elapsed time between two events. This is the same effect as the twin paradox, in which the twin who accelerates and travels ages less than the twin who stays home. Inside a black hole, the destination is fixed by the geometry, and struggling is acceleration, and acceleration costs you time. The longest possible life inside a black hole belongs to whoever relaxes completely. There is one more common belief that needs correcting, and correcting it changes what the whole scenario feels like. Being torn apart is not a property of the horizon. It is a property of small black holes. Tidal stretching happens because gravity is stronger at your feet than at your head, and the difference depends on how sharply the field changes over the length of your body. Near a 10 solar mass black hole, the horizon is only about 30 kilometers from the center, and the gradient across a human body is lethal hundreds of kilometers before you get there. You would be pulled into a thin stream of material long before the horizon. For a supermassive black hole, the horizon is millions of kilometers from the center, and over the length of a human body, the field barely changes at all. Crossing the horizon of Sagittarius A star would produce no sensation whatsoever. Nothing would happen. There is no membrane, no shudder, no change in the view. The only way you could know you had crossed would be to do the arithmetic. So the largest black holes are the ones you could enter intact, and they are also the ones that give you the longest interval inside to think about it. It is worth pausing on how strange that combination is. The most dangerous sounding object in the universe, at the largest sizes, has a boundary that is completely undetectable to anyone crossing it. There is no alarm. There is no last moment of warning. A crew could pass the point of no return in the middle of a conversation and finish the sentence without noticing anything at all. The horizon is not a wall in space. It is a fact about which futures remain available, and futures are not visible. Here is what those 66 seconds would actually contain. You cross, and nothing happens. The stars are still there. Behind you, where you came from, the outside universe is still visible. Light continues to fall in from outside, so the exterior does not go dark. It contracts. The sky behind you draws itself together into a bright circle, and the circle narrows as you descend, growing brighter and bluer as the light falling in with you gains energy. Ahead is the direction with nothing in it, and it takes up more and more of your field of view, not because there is a black object there, but because there is no longer any direction from which light can reach you. You have a minute. You could count it. You could think a complete thought, and then another. You could look back at a galaxy compressed into a shrinking coin of light and know that everything you ever knew is inside that coin. The tidal stretching arrives only in the final fraction of a second, when the geometry finally becomes sharp on the scale of a body, and by then, the interval is nearly over anyway. And the whole time, the arithmetic holds. If you had fired every engine you had, you would have had less. Two details of that minute are worth adding, because both are counterintuitive and both are solid. The first is that the interval does not depend on how fast you were going when you crossed. Arriving at the horizon at enormous speed does not buy you a longer run at the inside. It shortens it, for the same reason that thrusting does. The maximum belongs to the object that fell in from rest at a great distance and never touched a control. The second is that you cannot hover just inside and watch. Hovering is not available. It is not a matter of engine power, and it is not a matter of nerve. Holding position at a fixed radius inside the horizon would mean holding position in time, which is not a thing that any object can do. Every popular image of a ship parked inside a black hole, weighing whether to make a run for it, is describing something the geometry does not contain. There is no parking. There is only the descent, and how relaxed you are while it happens. What replaces the singularity is the open question, and nobody pretends otherwise. Essentially, every physicist expects that a quantum theory of gravity smooths the ending into something finite, and there is no agreement whatsoever on what that something is. Number 2 on this list is one specific proposal. But there is a classical description of the approach, and it is worth knowing because it is stranger than the smooth ending people imagine. Around 1970, 3 Soviet physicists, Vladimir Belinsky, Isaac Kalatnikov, and Evgeny Lifshitz, worked out how a generic spacetime behaves as it nears a singularity. The answer was not a smooth compression from all sides. It was an oscillation. Space stretches along one axis while squeezing along the other two. Then the axes switch. Then they switch again, faster and faster, in a sequence that never settles into a pattern. The switching is chaotic in the technical sense. Arbitrarily small differences in the starting conditions produce completely different sequences. The approach to a singularity, in the best available classical description, is a deterministic process that cannot be predicted in practice. It has been called the mixmaster behavior after a brand of kitchen appliance, which is one of the more grounded names ever attached to the end of a space-time. There is a reason that behavior matters beyond its own strangeness. If the approach to the singularity is chaotic, then whatever quantum theory eventually replaces the ending has to replace something wild rather than something smooth. The popular picture of matter being compressed steadily into a smaller and smaller ball, tidier and tidier as it goes, is not what the classical theory predicts. The classical theory predicts a region being kneaded, stretched one way, crushed the other, then swapped again, at an accelerating rate, without settling. The name attached to it, mixmaster, was coined by Charles Misner in 1969, and it was a joke about a kitchen appliance that has now outlived the appliance. It is also worth being honest about what all of this means for the question the list keeps returning to. If a path simply ends, then whatever was traveling along it, the star, the planet, the record of everything that fell in, has no continuation in the description. That is not the same as saying it was destroyed. It is saying that general relativity offers no account either way, and that anything asserted about the fate of that information is being asserted on the strength of some other theory, not this one. The singularity is not where the information goes. It is where the theory stops being able to say. That is the non-rotating case, and it is clean, one ending, in the future, unavoidable, and quite short. Real black holes spin. And spinning adds a second surface, well inside the first, where something considerably stranger than an ending is waiting. Number 4. The surface where prediction ends. A rotating black hole has two horizons. The outer one is the event horizon, the surface everyone knows about, the point past which no path leads back out. Some distance inside it lies a second surface, and what happens at that one is stranger than anything at the first. The second surface is called the inner horizon, or in the more revealing terminology, the Cauchy horizon. And the difference between the two can be stated in a single comparison. At the event horizon, you lose the ability to leave. At the inner horizon, physics loses the ability to predict. That deserves unpacking, because determinism is not usually thought of as something a theory can misplace. The idea has a long history in physics, and its clearest early statement came from Pierre-Simon Laplace at the end of the 18th century. Laplace imagined an intelligence that knew the position and motion of every particle in the universe at one instant, and observed that for such an intelligence, nothing would be uncertain. The future and the past would both be present to its eyes. That picture did not survive the 20th century intact. Quantum mechanics replaced the certainties with probabilities, but it survived in a modified form, and the modification matters. Quantum mechanics is still deterministic in its own terms. The quantum state evolves predictably. What is probabilistic is the outcome of a measurement performed on it. The underlying equations still take you from now to next. A Cauchy horizon is a different kind of failure entirely. It is not a place where outcomes become probabilistic. It is a place where the equations run out of input, where the future is not merely unknown but underdetermined, where the same starting conditions are compatible with different subsequent histories, and nothing in the theory chooses between them. That is a serious thing for a physical theory to contain, and it is why the surface has attracted so much attention from people who are not otherwise interested in black holes at all. General relativity is a deterministic theory. Specify the state of a region completely at one moment, the geometry, the matter, the fields, and their rates of change, and the equations determine what happens next, everywhere that can be reached from that region. This property is so basic that it is easy to forget it is a property rather than an assumption. It is what makes the theory a theory rather than a description. The region whose future is determined by a given set of starting data has a boundary, and that boundary is what mathematicians call a Cauchy horizon, after Augustin-Louis Cauchy and the mathematics of initial value problems. Past that boundary, the initial data are no longer sufficient. Something else is required to say what happens, and the theory does not supply it. New information can arrive from the singularity, and the equations have nothing to say about what that information is or what it does. Inside a rotating black hole, that boundary is a physical surface. It has a radius. It sits at a definite distance from the center, and in the mathematics of the Kerr solution, it is a perfectly ordinary-looking place with no local drama attached to it. An observer crossing it would, according to the classical solution taken at face value, notice nothing. They would simply pass out of the region where the universe is predictable into a region where it is not. The location of that second surface depends on how fast the hole is spinning, and the dependence is worth knowing because it explains why the previous entry could ignore it entirely. For a black hole with no rotation at all, the inner horizon shrinks all the way down and merges with the singularity, which is why the Schwarzschild case has only one surface and a clean, unavoidable ending. Add rotation, and the two horizons separate. The outer one draws inward slightly, the inner one moves outward from the center. The faster the spin, the further apart they are not. In fact, the closer together they come, until at the maximum possible rotation, the two surfaces meet and coincide. The same structure appears if you give the black hole an electric charge instead of a spin, in a solution worked out independently by Hans Reisner and Gunnar Nordström between 1916 and 1918, before anyone had a concept of a black hole to attach it to. Electrically charged black holes are not expected to exist in nature because any net charge attracts the opposite charge from the surrounding plasma and is neutralized very quickly. But the charged solution is far easier to calculate with than the rotating one, and it has the same two-horizon structure, which is why almost all of the foundational work on this problem was done on charged black holes and then argued to carry over to rotating ones. It is a useful reminder that a great deal of what is believed about the inside of the objects in our sky was established on a case that does not occur. Roger Penrose proposed in 1979 that this never actually happens. His argument was not that the mathematics is wrong, but that the mathematics is describing an idealization, and that any realistic black hole develops an instability at the inner horizon which destroys it before anything can cross. The proposal is called strong cosmic censorship, and it amounts to a claim that the universe does not permit observers to reach places where prediction fails. It is a conjecture. It has never been proven in general. And in 1990, Eric Poisson and Werner Israel worked out what the destroying mechanism actually is in a paper titled with complete restraint, Internal Structure of Black Holes. The mechanism is called mass inflation, and it is the reason this entry sits where it does. Here is how it works. Things continue to fall into a black hole for as long as it exists. Not just stars and gas, those are the dramatic cases and the rare ones. Mostly it is a thin, constant drizzle. Stray photons from distant galaxies, particles of the cosmic microwave background, gravitational waves passing through from events elsewhere, the occasional atom of interstellar hydrogen. The infall never stops. Over the lifetime of a supermassive black hole, that drizzle continues for a very long time indeed. All of that material falls inward, crosses the outer horizon, and continues. And as it approaches the inner horizon, the geometry does something to it that has no equivalent anywhere else. Recall what happens at the outer horizon. Light climbing out is redshifted, stretched, drained of energy. The inner horizon is the mirror image of that. Light falling in is blue-shifted, compressed, concentrated, its energy multiplied. And the multiplication factor is not large. It is unbounded, which produces the sentence that is the center of this entry, and it is worth stating carefully so that its shape is clear. The inner horizon is a surface at which the entire remaining future of the outside universe arrives at once. Everything that will ever fall into that black hole, over the whole of its existence, every photon, every particle, every wave, across billions or trillions or arbitrarily many years of exterior time, is compressed onto that surface and delivered in a single instant, at effectively unlimited energy. From inside, the exterior universe's future is not spread across time. It is stacked into a point. That is not a metaphor for something else. It is what the geometry does with infalling radiation, and it is why the inner horizon cannot survive. Poisson and Israel followed the consequence through. They considered a black hole with both an ingoing stream of material and an outgoing one, which any realistic black hole has, since infalling matter scatters, and they tracked a quantity called the Misner-Sharpe mass, a local measure of how much gravitating energy is enclosed at a given point. As the two streams pass through each other near the inner horizon, that quantity does not simply increase. It exponentiates on a timescale set by the surface gravity of the inner horizon, growing without any bound in a very short interval. Hence the name. The mass parameter inflates. And where the mathematics had shown a smooth surface that an observer could cross into unpredictability, there is instead a curvature singularity, sitting exactly where the boundary of determinism was supposed to be. The conjecture is thus defended by a wall, and the wall is made of the future. You cannot reach the place where physics stops predicting, because the place where physics stops predicting is sealed by a sheet built out of the entire remaining history of everything outside, arriving early and all together. The result did not stay a piece of analytic work for long. Through the 1990s and after, the collapse of charged scalar fields was simulated numerically, following the geometry all the way in, rather than approximating it, and the simulations reproduce the exponential growth cleanly. The mass function climbs through orders of magnitude in a span of time that, measured by an infalling clock, is short. The instability is not a subtle effect that appears only under special conditions. It is what these solutions do. There is a detail in the timescale worth stating, because it is the sort of thing that makes the process feel real rather than schematic. The rate of the exponential growth is set by the surface gravity of the inner horizon, a property of the black hole itself, not of the infalling material. The material only has to arrive. How violently the amplification runs is determined by the object in advance as a consequence of its mass and spin. In that sense, the wall is not built by what falls in. It is built by the geometry, and what falls in is merely the raw material. That is the picture. Now the complications, and there are several, because this is a live area rather than a closed one. The first complication is that the singularity produced by mass inflation appears to be weak in a specific technical sense. The curvature diverges. That part is not in dispute. But what does damage to a physical object is not the curvature at an instant. It is the accumulated distortion over the time the object is exposed to it. And because the divergence happens so quickly, the integrated effect may be finite. Amos Ory argued in 1991 that an observer could in principle cross such a singularity with finite tidal deformation rather than being destroyed by it. Squeezed, distorted, stretched, but not necessarily ended. If that is right, then the wall is real, and the crossing is survivable, which reopens the question rather than closing it. Strong cosmic censorship would be violated in the letter while being upheld in spirit, or the reverse, depending on which formulation you prefer. The second complication is that the calculation depends heavily on what the black hole is actually surrounded by. More recent work modeling astronomically realistic black holes, rotating, accreting, with genuine ingoing and outgoing streams rather than idealized test fields, finds the inflationary instability robust and violent in essentially all realistic cases. In those models, the inner horizon is not merely destroyed, it is replaced by a region where the streaming material reaches energies so extreme that the classical description of matter stops being appropriate long before the geometry does. The third complication is mathematical, and it is the one that keeps the subject alive. Strong cosmic censorship is not a theorem, and there are known circumstances in which it appears to fail. In universes with a positive cosmological constant, which, as far as anyone can tell, includes ours, the outside universe's future is not infinite in the relevant sense, because the accelerating expansion cuts off the flow of infalling radiation. Less material arriving means less blue shift, means a weaker instability, and there are parameter ranges in which the inner horizon appears to survive in a form smooth enough to cross. This has been studied intensively over the last decade, and it is not resolved. There is a fourth complication, and it is the one that connects this entry to the rest of the list. The argument that the entire future of the outside universe arrives at the inner horizon assumes there is an entire future to arrive, that the black hole persists indefinitely, and that material keeps falling in the whole time. But black holes do not persist indefinitely. They evaporate, slowly at first and then not slowly, and when the object is gone, there is no more infall to deliver. The exterior history that gets compressed onto the inner horizon is therefore finite, not infinite, and the amplification, while enormous, is bounded. Whether that bound is low enough to matter is a genuine open question, and the numbers are not encouraging for anyone hoping to make the crossing. The lifetime of a supermassive black hole against evaporation runs to something like 10 to the 100th years. Even a finite history of that length, compressed into a single arrival, is not a survivable quantity of energy by any ordinary standard. It is worth being concrete about what that energy would do to something made of atoms. An object crossing into that region is not encountering a strong gravitational field in the usual sense. It is encountering radiation, the accumulated infall of an age, arriving with wavelengths compressed past every scale physics has a name for. Long before the geometry did anything to the object, the radiation would have taken it apart into constituents, and taken the constituents apart in turn. The question of whether the tidal distortion at the singularity is technically finite becomes somewhat academic when the approach to it is a bath at energies above anything the universe has contained since its first fraction of a second. It is worth separating two conjectures that sound alike and are not. Weak cosmic censorship is the proposal that singularities are always hidden behind event horizons, so that no observer outside ever encounters one. It protects the outside universe from unpredictability. Strong cosmic censorship is the proposal that no observer anywhere ever crosses a Cauchy horizon into a region where the equations lose their grip. It protects determinism itself. Neither has been proven. Both are believed by most of the field, for the reason that the alternatives are unattractive, rather than because anyone has closed the argument. And it is worth noticing what that means. The claim that the universe is predictable is not, at present, a result. It is a hope with a great deal of supporting evidence. It should also be said that not everyone regards the possible failure of strong cosmic censorship as a disaster. There is a minority view, argued seriously, that a region where the equations do not determine the future is not a catastrophe for physics, but a boundary condition, that the theory would simply require additional input there, in the way that any theory requires input at a boundary, and that nothing incoherent follows. On this view, the discomfort is aesthetic rather than logical, and the insistence that the universe must be predictable everywhere is a preference inherited from the 18th century rather than a requirement derived from anything. The majority view is the opposite, that a theory which permits observers to reach regions where it stops applying is telling you something about its own limits, and the honest response is to find the better theory rather than to accept the gap. Both positions are held by people who understand the mathematics completely. The disagreement is not about the equations. It is about what a physical theory is for. One more consequence, rarely stated, and it belongs here because it makes the whole thing concrete. Suppose you fell into a large rotating black hole, survived the crossing of the outer horizon without incident, as the geometry says you would, and continued inward. As you approached the inner horizon, you would look back the way you came. And the light arriving from behind you would be arriving faster and faster, not louder exactly, but compressed, with the whole outside universe running forward at an accelerating rate. Stars would be forming and dying in the time it took to notice them. Galaxies would drift apart and dim. The exterior sky would rush through its remaining history and deliver it, and the last thing you would ever see would be everything that was ever going to happen, arriving in a single flash of blue. That is what is waiting at the second horizon, according to the equations, and it is why nobody expects the second horizon to be a place you can visit. If anything did survive it, though, the mathematics says it would arrive somewhere the rest of physics has no word for. Number 3. The ring, and the region on the other side of it. In a black hole that is not rotating, the singularity is a moment. In a black hole that is rotating, which is to say, in every black hole that actually exists, it is a ring. The rotation flings the singularity outward from the center into a circle lying in the equatorial plane, with a radius set by how fast the object spins. For a slowly rotating hole, the ring is small. For one spinning at the maximum rate permitted, the ring is as large as the horizon radius itself. And the ring has a property that the point-like version does not. It has a hole in the middle. In the mathematics of the Kerr solution, that hole leads somewhere. The size of the ring is worth making concrete, because it is one of the few quantities in this entry that can be. The radius is the object's angular momentum, divided by its mass and by the speed of light, which for a rapidly spinning hole works out close to the radius of the horizon itself. For a black hole of 10 solar masses spinning near its limit, that is a circle roughly 30 kilometers across, the size of a city, holding the mass of 10 suns, with the curvature of the description going to pieces along its circumference. For the object at the center of our galaxy, it would be a ring some millions of kilometers wide. Neither has any thickness. The ring is a curve, not a wire, and the region enclosed by it is an ordinary two-dimensional disk that anything could in principle pass through. That is the geometry. A circle where the theory fails, and inside it, an opening. This is the point on the list where the material becomes genuinely difficult to present honestly, because what the equations contain is extraordinary, and what the equations are describing is almost certainly not a real object. Both of those things have to be held at once. So here is the structure of this entry. First, what the solution says, in full, without hedging. Then the 3 separate reasons that almost nobody believes it describes anything you could visit. Then a recent development that suggests the question is less settled than it has looked for 60 years. What the solution says is this. Approach the ring in the equatorial plane, and you reach the singularity, curvature without bound, the end of the description, the same kind of ending as the non-rotating case. But approach it through the middle, passing through the ring rather than into it, and the mathematics continues. There is more space-time on the other side. In the standard coordinates, it is labeled with negative values of the radial coordinate, which is a way of saying the geometry has been extended past what a radius normally means, and the region it opens into is a complete, asymptotically flat universe, a place with its own distances, its own infinity, its own everything. Before those features, there is a property of the rotating singularity that changes the character of everything in this entry, and it is easy to miss because it is stated in technical language. The singularity of a non-rotating black hole is spacelike, which is the formal way of saying it is a moment in time. The ring singularity of a rotating black hole is timelike, which is the formal way of saying it is a place. The consequence is direct. A place can be avoided. Once inside the inner horizon of a rotating black hole, an object is no longer on rails. The forced march toward the ending, which was the whole character of the interior in the non-rotating case, stops being forced. You can steer. You can miss the ring entirely, orbit it, approach it and pull away. The ring is a thing in a region rather than a fate at the end of one, and in the geometry of the classical solution, there is nothing compelling anything to touch it. That is why the Kerr interior has a structure worth discussing at all. In the Schwarzschild case, the interior has one story, and it is over in microseconds. In the Kerr case, the interior is a region with an interior of its own, with choices available in it and a door in the middle. And it has two features that occur nowhere else in physics. The first is that gravity there is repulsive. The same mass that attracts everything on this side pushes everything away on that one. An object entering the negative region is not pulled toward the ring, it is pushed away from it, and it can travel out into that region and never come back. The second is that the region contains closed, time-like curves. That phrase deserves to be stated in plain language because the technical vocabulary muffles it. A time-like curve is a path that a physical object could follow, slower than light, forward through its own time, a legal trajectory. A closed one returns to its own starting point, not just in space, but in time. It arrives back at the event it departed from. This is time travel, in the strict sense of the term. Not a wormhole shortcut, not a relativistic aging effect, not a philosophical puzzle about the direction of entropy. A world line that a spaceship could follow, which comes back to its own beginning. Brandon Carter worked out the global structure of the Kerr solution in 1968 and identified both features. And the closed time-like curves are not tucked away in some remote corner of the geometry where they could be dismissed as marginal. In the negative radius region near the ring, they thread through every event. By moving along them, an object could reach any point in that region, at any time, past or future. There is a further detail about that region, which makes it stranger still. On our side of the ring, the singularity is hidden. It sits behind two horizons, and nothing outside can see it or be affected by it. On the far side, in the negative region, there are no horizons at all. The ring is visible from anywhere in that universe. It is what physicists call a naked singularity, a place where the description fails, in plain view, with no surface separating it from everything else. The prohibition on naked singularities in our own universe is a conjecture too, weak cosmic censorship, mentioned in the previous entry. People have tried repeatedly to violate it. The standard approach is to take an existing black hole and try to overspin it, throw in material carrying more angular momentum than the object can support, so that the horizons vanish and the ring is exposed. Robert Wald showed in 1974 that the attempt fails in the most direct version. A particle carrying enough angular momentum to do the job is repelled by the black hole before it can be absorbed. Later and more sophisticated attempts, using finely tuned matter and accounting for the object's own back reaction, have generally failed in the same manner. The universe appears to be defending itself, and once again, nobody has proven that it must. Consider the position that puts the field in. Roy Kerr had written down a one-page solution in 1963 describing the gravitational field of a spinning mass, an ordinary, physical, astrophysically necessary object. 5 years later, when someone extended that solution as far as the mathematics allowed, it turned out to contain a region where causality does not hold. And there was no obvious principle available to remove it. and it cannot be waved away as one exotic solution among many. There is a uniqueness theorem, assembled over roughly a decade by Werner Israel, Brandon Carter, David Robinson, and others, establishing that the Kerr solution is the only possible stationary, rotating, uncharged black hole in general relativity. Not the simplest, the only one. Whatever settles down after a star collapses or after two black holes merge is a Kerr black hole, with no freedom left in it beyond its mass and its spin. So the causality-violating region is not a curiosity attached to an unrealistic special case that could be replaced by a better model. It is attached to the unique solution, the one every real object in the sky is described by. If you want to remove it, you have to remove it by an argument about which parts of the solution are physically realized, which is precisely the argument that follows. It is worth also saying what a closed time-like curve would and would not permit, because the phrase invites a particular kind of confusion. General relativity is not a theory in which events happen and are then revised. A space-time with closed time-like curves is a single, fixed, four-dimensional object, and the curve is simply a path in it that closes. Anything on that path was always on it. The traveler who goes around and arrives at their own departure was present at their own departure the first time, because there is no first time. There is one history, and it contains the loop. That requirement is sometimes called the self-consistency principle, associated with Igor Novikov, and it has a specific consequence. Paradoxes do not arise, because inconsistent histories are simply not solutions. What is unsettling about closed time-like curves is not that they permit contradiction. It is that they permit events with no cause anywhere in their past, a fact, a message, an object, that exists only because it exists, arriving from a loop with no beginning. The physics is consistent. It just contains things that were never made. Now the three reasons almost nobody believes you could go there. The first reason is about idealization. The maximal extension of the Kerr solution, the full mathematical object with the ring passage and the negative region and the causality violation, describes an eternal black hole. Not one that formed. Not one that will end. An object that has existed forever, in isolation, rotating steadily, in an otherwise empty universe. Real black holes are made by collapsing stars, and the spacetime of a collapsing star does not contain the extension. The star is in the way. The region beyond the ring exists in the idealized solution, and there is no reason to think it exists in any spacetime that was ever built. This is a common situation in general relativity, and it is worth understanding, because it recurs. The equations often permit more than nature constructs. Solutions can be extended beyond the region their physical setup justifies, and the extension is mathematically legitimate and physically empty. The classic parallel is the white hole region and the second universe that appear in the full extension of the Schwarzschild solution. They are there in the mathematics, and no collapsing star produces them. It helps to picture what the extension looks like when it is drawn out properly. Physicists represent these geometries with diagrams that compress an infinite spacetime onto a finite page, so that the causal structure, what can reach what, is visible at a glance. The diagram for a non-rotating black hole made by a collapsing star is simple. A star, a horizon, an ending, and nothing else. The diagram for the eternal, idealized version is not simple. It contains a white hole, a second exterior universe connected to ours through a bridge that closes too quickly for anything to cross, and a second ending. None of that is thought to exist. It is what you get when you take a mathematical object and extend it as far as it will go, without asking whether anything ever built it. The diagram for the eternal, rotating case is more elaborate still. It is not one universe with a hole in the middle. It is an infinite chain: exterior, horizon, inner horizon, ring, negative region, and then another exterior, and another, repeating without end in both directions, each connected to the next through the passage in the middle of a ring. 60 years of textbooks have reproduced that chain, always with a footnote, observing that no known process produces it. The second reason is the previous entry on this list, and it is the decisive one. To reach the ring, you have to cross the inner horizon. And if mass inflation does what Poisson and Israel showed it does, that crossing is sealed by a wall built out of the compressed future of the exterior universe. The interior of a real rotating black hole is not the interior of the textbook Kerr solution, and the difference between them begins at exactly the door to the ring. Everything in this entry is on the far side of that door. The third reason is a conjecture with a name that gives away its author's sense of humor. In 1992, Stephen Hawking proposed the chronology protection conjecture, that the laws of physics conspire to prevent closed time-like curves from forming, and that they do so specifically to keep the universe safe for historians. The proposal was not merely a preference. Attempts to construct a working time machine within general relativity have a persistent habit of failing in the same way. When you calculate the behavior of quantum fields in a spacetime that is about to develop closed time-like curves, the fields tend to produce an unbounded energy density right where the curves are about to close, and that energy feeds back into the geometry and destroys the arrangement before it can be completed. It looks very much like a defense mechanism. It has never been proven to be one. That line of work has a peculiar origin story, and it is worth telling. In the mid-1980s, Carl Sagan was writing a novel and wanted a method of interstellar transport that a physicist would not laugh at. He sent the manuscript to Kip Thorne. Thorne looked at the problem, decided the black hole Sagan had used would not work, and suggested a wormhole instead. Then, with his students Michael Morris and Ulvi Yurtseva, worked out what a traversable wormhole would actually require, and published the results. In the course of that analysis, they noticed that a wormhole with its two mouths in relative motion would function as a time machine. The modern physics literature on closed time-like curves begins in a direct and traceable line with a novelist asking for a plausible plot device. Frank Tipler had already proved, in 1974, that any attempt to build closed time-like curves in a finite region of spacetime, subject to reasonable conditions on energy, forces a singularity to appear. Which is to say, the universe permits time travel only in company with the one thing physics cannot describe. If you did make the passage, and if the solution described anything real, what you would arrive in is difficult to picture for a reason that has nothing to do with exotic physics. It is not a cave. It is not a tunnel. It is an entire universe, extending outward in every direction to its own infinity, empty except for the ring you came through. And the ring, behind you, is now the only thing in that universe with a mass, pushing rather than pulling, so that whatever direction you chose, you would drift away from it, indefinitely, into open space that nothing occupies. The one feature of that place is a circle of failed description, visible from everywhere, receding. Whether anything at all is there is unknown and probably unknowable. But it is worth noticing that the mathematics does not describe a small hidden chamber. It describes somewhere larger than the place you left. So the ring passage is a region in a solution nobody thinks is realized, behind a wall nobody thinks is passable, containing a structure most physicists believe is forbidden by a principle nobody has proven. That would be a tidy place to end the entry. Except that in December of 2023, the man who wrote the solution, published an objection. Roy Kerr, by then in his late 80s, released a paper arguing that the standard conclusion about singularities inside rotating black holes has been misapplied, including in his own solution. The argument concerns exactly what the singularity theorems establish. As covered at number 5, what Penrose proved is geodesic incompleteness, that certain paths end after a finite interval. What is usually assumed, and stated in textbooks, is that this incompleteness must correspond to a place where curvature becomes unbounded. Kerr's contention is that this step has never actually been proven, that finite-length paths can end for reasons other than infinite curvature, and that the assumption that Kerr black holes contain physical singularities is an assumption rather than a result. The title of the paper is, "Do Black Holes Have Singularities?" His specific target is a step that appears in almost every textbook treatment. The theorems establish that certain light rays inside a black hole have finite affine length, that following them you run out of path. The standard reading is that they run out of path because they have hit a place of unbounded curvature. Kerr's argument is that a light ray can terminate for reasons that have nothing to do with curvature blowing up, that the Kerr solution's own structure provides examples, and that in 6 decades nobody has closed the gap between the theorem and the conclusion drawn from it. The claim is contested. Several responses have argued that it does not survive scrutiny. It is not included here because it is likely to be correct, and this episode is not going to tell you that the textbooks are wrong. It is included because of what it says about the state of the subject. The interior of a rotating black hole is unsettled enough that the person who first wrote down its geometry can, 60 years later, raise a serious objection to what the field believes is in there, and be argued with, rather than dismissed. 60 years, 1 page of algebra, and the question of what is at the bottom of it is still open. Every entry so far has assumed there is a singularity at the bottom of all this. The next one assumes there is not. Number 2, the bounce, and the object that is not a hole at all. Every entry so far has taken for granted that something inside a black hole goes wrong, that the collapse continues until the description fails, and that the failure is the ending. There is a serious research program built on the opposite assumption, that the collapse stops, that nothing infinite is ever reached, and that what sits inside a black hole is a small, extremely dense, entirely finite object, and that the object is not permanent. That what we call a black hole is not a thing but a stage in a process, and the process is a bounce. The proposal has a name, given to it in 2014 by Carlo Rovelli and Francesca Vidotto. They called it a Planck star. The argument rests on a distinction that is easy to skim past and that carries the entire idea, so it is worth stating slowly. The scale at which quantum effects on gravity are expected to matter is usually quoted as a length, the Planck length, about 10 to the minus 35 meters, which is smaller than a proton by roughly 20 orders of magnitude. Because that number is so small, the standard assumption has been that quantum gravity only becomes relevant at the very end of a collapse, when the material has been compressed almost to nothing, and that everything before that point is safely classical. Rovelli and Vidotto pointed out that the trigger is not the size, it is the density. Quantum gravitational effects switch on when the density reaches the Planck density, and density depends on how much mass you have as well as how tightly it is packed. A collapsing star has an enormous amount of mass. It therefore reaches the critical density, while it is still far larger than the Planck length, larger by a factor that grows with the mass involved. For a stellar mass black hole, the core at which the quantum effects become important would be somewhere in the neighborhood of the size of an atomic nucleus. That is still very small. It is also enormously larger than the scale everyone assumes. And the difference matters, because a structure of that size is a physical object with properties rather than a mathematical point with none. It is worth saying where that repulsion is supposed to come from, because otherwise it sounds like a convenience introduced to get the answer somebody wanted. In loop quantum gravity, space is not a smooth continuum that can be subdivided indefinitely. Geometry is quantized. Areas and volumes come in discrete units, with a smallest non-zero value, the way electric charge comes in discrete units, and energy levels in an atom come in steps. There is no such thing as half of the smallest area, in the same way that there is no such thing as a third of an electron's charge. If that is true, then a collapse cannot proceed past the point where the available geometry runs out of subdivisions. Something has to give, and what gives is the inward motion. The resistance is not a force applied to matter. It is the geometry declining to have a smaller version of itself. The same mechanism, applied to the universe as a whole rather than to a star, produces what is called the Big Bounce, a cosmology in which the Big Bang is not a beginning, but a rebound from a previous contracting phase. That is the more famous application of the idea, and the Planck star is its local counterpart, the same refusal, at the same density, inside one collapsed object instead of everything at once. At that density, in this framework, the collapse stops. Quantum gravitational pressure, a repulsion with no classical counterpart, arising from the discreteness of the geometry itself, pushes back hard enough to halt the infall. And then the material rebounds. The immediate objection is obvious, and the answer to it is the most satisfying part of the proposal. We do not observe black holes bouncing. We observe black holes sitting in the middle of galaxies for billions of years, doing nothing of the kind. The answer is time dilation, and here the extreme numbers work in the theory's favor rather than against it. The bounce is quick, as measured by the material doing the bouncing. A fraction of a second, at the core. But time near a black hole does not run at the same rate as time far away, and the discrepancy near the horizon is not a modest correction. It is enormous, and it grows without limit as you approach the surface. A process that takes a fraction of a second in there is stretched, as seen from out here, over an interval comparable to the black hole's entire evaporation lifetime. It is worth grounding that claim in a case where the effect has been measured, because time dilation has a reputation for sounding like a license to say anything. It is not theoretical. Clocks on satellites in orbit run measurably faster than clocks on the ground, by tens of microseconds a day, and the correction has to be applied continuously, or satellite navigation fails within hours. That is the effect produced by the Earth, which is a weak source of gravity by any standard. Near the horizon of a black hole, the same effect is not measured in microseconds per day. It has no upper bound at all. The closer to the surface, the larger the ratio, without limit. So a process that takes a tenth of a second at the core, viewed from a position where the ratio is large enough, is not stretched into minutes or years. It is stretched into whatever interval the geometry dictates, and the geometry near a black hole horizon dictates intervals that make the age of the universe look brief, which produces a way of describing black holes that reframes everything. What we call a black hole is a long exposure of a very brief event. Not a slow process. A fast one, watched through a lens that stretches it across the age of the universe and beyond. The photograph taken in 2019 was, on this reading, a snapshot of a moment in the middle of a rebound that from the inside has barely begun. What emerges at the far end, in this picture, is a white hole. That is the time reverse of a black hole, a region that nothing can enter and from which material emerges. White holes are not forbidden by any law of physics. They are perfectly good solutions of the equations. They simply are not produced by any process anyone knows of, which is why they have spent most of a century as a curiosity in textbooks rather than a candidate for anything. In 2014, Hal Haggard and Ravelli showed that a metric exists which describes exactly this: matter collapsing into a black hole, a quantum tunneling event in a finite region, and matter emerging from a white hole afterward, with the classical equations of general relativity satisfied everywhere except inside that finite region. The transition does not require the singularity. It requires a small region where the classical description hands over to something else and then hands back. There is a second reason the picture is attractive, and it has nothing to do with singularities. It offers a route out of the information paradox that does not require anything clever. The paradox, in the form that has driven most of this list, is that information falls in and the radiation coming out appears not to carry it. Every proposed solution has had to find a way for the information to get into that radiation, and the technical difficulty of doing so is what produced the firewall argument at number 7 and the calculations that will close this list at number 1. In the bounce picture, the information does not have to get into the radiation at all. It goes in one side and comes out the other. Whatever fell in emerges when the white hole opens, scrambled and delayed by an interval that is enormous from outside and brief from within, but not destroyed and not encoded anywhere exotic. The books balance by the simplest available means. Nothing was ever lost. It was in transit. Whether that works in detail is contested. Critics have pointed out that a remnant small enough to be left at the end of evaporation may not have the capacity to hold everything the black hole swallowed, and that white holes in the classical theory are unstable to the point of being unbuildable. Supporters answer that the interior volume result discussed at number 6 provides exactly the room required, a small surface with an enormous and still growing interior, which is the shape of thing the argument needs. That is a genuine dispute between serious positions, and it is not settled. It is also worth noticing a dispute in which two entries on this list are being used against each other. The framework has an observational hook, and it is worth stating both what it predicts and what has come of it. Small black holes formed in the first moments after the Big Bang, primordial black holes, which may or may not exist, would have been evaporating ever since. Some of them would be reaching the end of the process about now. If the bounce picture is right, the end of the process is not a quiet fade but an emergence, and it would produce a signal at a characteristic wavelength that can be calculated from the mass. Aurélien Barraud and Ravelli laid out that phenomenology in 2014. Nothing has been detected. The predicted signals fall in bands that have been surveyed, which makes the absence a genuine constraint rather than an untested claim. The framework also generates a dark matter candidate, small remnants left behind by bounces, stable and nearly inert, drifting through the galaxy in numbers large enough to matter. That too has been explored, and that too has no confirming evidence. Now the honest accounting, because this entry sits at number 2 on the strength of how much it would change rather than on the strength of the evidence for it. Loop quantum gravity, the framework that produces the Planck star, is not an established theory. It is one of several serious candidate approaches to combining gravity with quantum mechanics. It has not been confirmed experimentally in any respect, and there is no consensus in the field that it is correct. The Planck star is a model constructed inside that framework. It inherits every uncertainty the framework has, and it adds some of its own. There is also a related family of proposals that goes further, and it is worth naming here because it sets up the final entry. In the late 1980s, Valery Frolov, Moisei Markov, and Vyacheslav Mukhanov worked out models in which the interior of a black hole, rather than bouncing back into the universe it came from, expands into a region of its own, a space-time that inflates behind the horizon, connected to our universe through a narrow throat, growing into something with its own volume and its own history. From outside, it would look like an ordinary black hole of a certain mass. From inside, it would be a universe. That idea was not built inside loop quantum gravity, and it does not depend on it. It relies only on the possibility that at extremely high density, matter behaves in a way that drives expansion rather than continued collapse, which is exactly the behavior cosmologists already invoke for the earliest moments of our own universe. The mechanism is not exotic by the standards of cosmology. What is exotic is where it is being applied. The broader idea, that black holes might have no singularity at all, is much older and much less tied to any one approach. In 1968, James Bardeen presented a solution with a proper event horizon and a smooth, finite core in place of a singularity at a conference in Tbilisi. It was never published in a journal, which is why it circulated slowly and why the class of solutions it launched, now called regular black holes, took decades to be taken seriously. Others have been constructed since, by various routes. None of them has observational support either. There is one place where a test may eventually be possible, and it is worth mentioning because it is the only genuinely promising route on the horizon. When two black holes merge, the object left behind rings. It oscillates and settles, radiating gravitational waves at a set of frequencies determined entirely by its mass and spin. Those frequencies are a fingerprint of the geometry just outside the horizon. If a black hole is not quite a black hole, if it has a surface or a slightly different structure near the boundary, the ringing changes, and in some models a faint series of repeat pulses arrives afterward, as waves bounce between the object and the surrounding curvature instead of disappearing inward. Searches for exactly that kind of delayed repeat have been carried out on existing gravitational wave data. Nothing convincing has been found, and the claims that have been made have not survived scrutiny. But the detectors are improving, the catalogue of mergers is growing quickly, and this is one of the few places where a proposal about the interior of a black hole makes contact with an instrument that exists. So what is the status of number 2? It is a coherent, actively developed proposal, made by people of standing, which contradicts most of the rest of this list, and which nobody can currently test. It is also worth being clear about why it is so hard to test, because the difficulty is structural, rather than a matter of building a better instrument. Everything distinctive about the proposal happens either behind a horizon where no signal can reach us, or at the end of an evaporation process that for every black hole we know about lies further in the future than the current age of the universe by an almost uncountable margin. The only cases that could produce a signal now are primordial black holes of a very specific mass, and it is not established that primordial black holes exist at all. The test requires an object that may not be there, doing something at a moment nobody can predict precisely, at a wavelength that depends on parameters nobody has measured. That is not a reason to dismiss the idea. It is a reason to hold it exactly as loosely as its own authors do. Rovelli has been consistently careful in print about what is derived and what is conjectured, which is more than can be said for how the proposal is sometimes reported. What makes it belong this high is the size of the revision it would represent. If the bounce picture is right, then the singularity discussed at number 5 does not exist. The inner horizon at number 4 is a feature of a solution that gets replaced before it matters. The ring at number 3 and the region beyond it are artifacts of a classical description that never applies. Black holes are not permanent. The objects photographed in 2019 and 2022 are not endings but middles, watched at an enormously reduced speed, and every one of them is on its way back out. Here is what the moment would be, from the inside. The material arrives. Not gradually. The last stage of a gravitational collapse is the fastest part of it, and by this point, the infall is a torrent. The density climbs through everything ordinary matter can be, past the density of an atomic nucleus, past anything a neutron star holds, and keeps going. And then it meets something that is not a force in any sense, that has a name outside this framework, the geometry itself refusing to be compressed any further, because at that scale it is not a smooth thing that can be compressed, but a discrete one, with a smallest available size. The inward motion stops. Then it reverses. From the point of view of the material, that reversal takes less time than a heartbeat. Outside, in the galaxy, in the ordinary universe with its stars and its long, slow processes, the same interval covers the formation and death of every star that will ever form, the drifting apart of galaxies past the point of visibility, and the cooling of everything toward the dark. The bounce is not slow. Everything else is... Which leaves one question that this list has been circling from the very beginning. Not what is inside a black hole. Whether inside is the right word. Number 1, the possibility that there is no inside. The last entry on this list is not a thing hiding inside a black hole. It is a proposal about what the word inside means, and it is simultaneously the most conservative and the most disquieting item here. It begins with the accounting fact established at number 8, which was left deliberately unfinished. The information capacity of a black hole is set by the area of its horizon, not by the volume it encloses. 1 bit for every 4 Planck areas of surface, and no more, no matter what is in there. That is not how anything else works. A hard drive holds more if you make it thicker. A library holds more books if you add a floor. A warehouse holds more crates if you extend it backward. Everything we have ever built to store anything stores it in a volume, and capacity grows with the third power of the size. A black hole's capacity grows with the second power. It is written on the surface. It is worth making that capacity concrete, because the numbers are absurd in both directions at once. A Planck area is about 10 to the minus 70 square meters. So a black hole with a horizon the size of a dinner plate would store something on the order of 10 to the 69 bits. Every hard drive, server farm, photograph, book and recorded conversation ever produced by the human species amounts to something in the region of 10 to the 23 bits. The dinner plate exceeds all of it by a factor with 46 zeros in it. And ordinary matter is nowhere near that ceiling. The Earth, treated as a region of space, stores something like 10 to the 67th times less information than its own surface area would in principle permit. The bound is not a constraint that anything ordinary is pressing against. It is a ceiling so high that only one kind of object in the universe ever reaches it, and that object reaches it exactly. For a long time, this looked like a peculiarity of black holes, a strange feature of one strange object to be noted and set aside. In 1993, Gerard Hooft suggested taking it literally. His argument was a counting argument, and it is worth following because it does not require any exotic assumption. Suppose a region of space could store more information than a black hole of the same size. Then you could load that region with data, add just enough mass to collapse it into a black hole, and end up with a black hole holding less information than went in. Information would have been destroyed, and the thermodynamics would fail. So no region of space can hold more information than a black hole of the same dimensions, which means the maximum information content of any region is set by the area of its boundary, rather than by its volume. And Hooft took the next step, which is the one everything else follows from. If the boundary is where the capacity lives, perhaps the boundary is where the physics lives. Perhaps a region of space can be described completely by degrees of freedom living on its surface, one per Planck area, with the interior emerging from that description rather than being fundamental. Leonard Susskind developed the idea the following year and gave it the name it has carried ever since, in a paper titled "The World as a Hologram." The word hologram is doing precise work there, not decorative work. A hologram is a two-dimensional recording, a pattern of interference on a flat plate, which contains the complete information about a three-dimensional scene, and which reproduces that scene, with depth, when it is illuminated correctly. The depth is not stored as depth. It is stored as a pattern on a surface, and the third dimension is recovered from the pattern. The claim was that the universe might be like that. Not that it looks like a hologram, or resembles one poetically. That the mathematics has that structure, everything happening in a volume, encoded on the boundary of that volume, with the two descriptions equally complete. For 3 years it was a suggestive idea without a working example. Then, in 1997, Juan Maldacena produced one. What Maldacena showed was that a specific theory of gravity in a specific kind of space-time is exactly equivalent to a quantum theory without gravity living on that space-time's boundary. Not approximately equivalent. Not equivalent in some limit. The same physics, described twice, in different numbers of dimensions, with a dictionary translating every question in one description into a question in the other. Anything that happens in the interior, a star, a collision, a black hole forming and evaporating, corresponds to something happening in the boundary theory, which contains no gravity at all and no extra dimension for anything to happen in. Neither description is the real one. That is the part that takes time to absorb. There is no fact of the matter about whether the universe in that model is three-dimensional with gravity or two-dimensional without it. Both are complete. The dimension is not fundamental. It is a way of organizing the information. The paper became one of the most cited in the history of theoretical physics, and it turned holography from a philosophical proposal into a calculational tool that thousands of people use. It is fair to ask why anyone believes it, given that it cannot be tested against an experiment. The answer is that it has been checked extensively in the only way available, by computing the same quantity twice, once in each description, and comparing. Those checks are not trivial. A calculation that is simple on one side is typically extremely difficult on the other. That is the point of having a duality, and it is why the correspondence gets used as a tool. Physicists have taken problems in the behavior of strongly interacting matter, translated them into questions about black holes, solved the black hole version, and translated back. The answers come out matching, in case after case, for quantities that have no business agreeing unless the correspondence is real. There is a phrase that gets used for the consequence, and it is worth defining rather than letting it drift past. Space-time is emergent, meaning the geometry of a region, its distances, its dimensionality, is not a fundamental input to the description. It arises from the pattern of entanglement among the degrees of freedom on the boundary. Change the entanglement, and the geometry changes. Remove the entanglement between two halves of the boundary, and in the interior description, the two corresponding regions of space come apart. The connection between them, the very fact that you can travel from one to the other, ceases to exist. That result, worked out in the 2010s, is one of the strangest things in modern physics, and it is not speculative in the setting where it applies. Distance, in that setting, is a measure of correlation. Two places are near each other, because their descriptions are entangled. Space is what entanglement looks like from the inside, which is the frame in which the black hole interior question finally makes sense. Asking what is inside a black hole is asking about a region of emergent spacetime. And the answer that comes back is not that the region is empty, or full, or dangerous. It is that the region is a way of reading a pattern held somewhere else. Now apply it to the question this list has been asking. Under holography, the interior of a black hole is not a location containing objects. It is a pattern in a system of degrees of freedom living on the surface, in the same way that the depth in a hologram is a pattern on a plate. There is no smaller thing to find in there. There is a code, and the code is on the outside. That would be a strong claim to make on the strength of an analogy. Between 2019 and 2020, it stopped being an analogy and became a calculation. The problem to be solved was the one described at number 7, the Page curve. If black hole evaporation is unitary, the entanglement entropy of the outgoing radiation has to rise and then fall back to zero. Hawking's original calculation gives a curve that rises and keeps rising, which is the information paradox in one line. For 45 years, nobody could produce the correct curve from a gravitational calculation. The failure was the paradox. Then Geoffrey Pennington, working alone, and independently a group including Ahmed Almheri, the same Almheri whose name is on the firewall paper, showed how to get it. The key was to include, in the calculation of the radiation's entropy, a region of spacetime that has no business being included, a piece of the black hole's interior. In the technical vocabulary, it is called an island. Past a certain point in the evaporation, the correct calculation says that the interior of the black hole is not a separate region whose contents are hidden from the radiation. It is part of what the radiation describes. The curve comes out right. The information is not destroyed, and it does not exactly escape either. It turns out to have been on the outside all along. It is worth pausing on how strange that statement is when it is unpacked. The island is a region of space-time behind the horizon, genuinely inside, in the ordinary sense, in a place from which no signal can reach the outside. And the calculation says that if you want to know the entropy of the radiation that has already left and is drifting away across the galaxy, you must include that interior region in the accounting, as though it were part of the radiation rather than part of the whole. There is no signal traveling from the island to the radiation. Nothing is crossing the horizon in the wrong direction. The claim is not about transmission. It is about identity. After a certain point in the evaporation, the interior region and the distant radiation are not two systems that exchange information. They are two descriptions of the same degrees of freedom, and treating them as separate is the error that produced the paradox. There is a companion idea sitting underneath that, proposed by Maldacena and Susskind in 2013 and mentioned earlier on this list. Their suggestion was that entanglement and geometry are the same thing, that two entangled systems are connected by a bridge in spacetime, so that the correlation between a particle here and a particle far away is not a mysterious link across a gap, but a short connection through a geometry we do not usually draw. The slogan is that Einstein-Rosen equals Einstein-Podolsky-Rosen, the wormhole and the entanglement, published in the same year by overlapping authors, are one phenomenon described twice. If that is right, the island stops being paradoxical and starts being obvious. The interior is inside the radiation because it is connected to the radiation, geometrically, through a structure that does not appear on any map of space drawn the usual way. The follow-up work, involving a technique in which one sums over space-time geometries that connect otherwise separate copies of the same black hole, replica wormholes in the jargon, put the result on firmer ground and drew in a large part of the field. It is regarded as the most significant progress on the information paradox since the paradox was posed. It is also, and this must be stated, a set of results obtained in models with particular properties, and the field is still working out how far it generalizes. Which brings us to the necessary caveat, and it needs to be made plainly rather than buried. Maldaceno's exact correspondence is established for a space-time with a negative cosmological constant, a universe that curves in on itself and possesses a boundary at infinity, which is what the boundary theory lives on. Our universe does not appear to be that. Measurements of distant supernovae and of the cosmic microwave background indicate a small positive cosmological constant, an expansion that is accelerating, and no boundary of the required kind. Whether holography extends to a universe shaped like ours is an open research problem. Many physicists expect that it does, in some form. Nobody has shown it. So the honest summary of number 1 is this. The best understood model of quantum gravity anyone has says that the interior of a black hole is an encoding of information on its surface, and that model does not describe the universe we live in, and no one knows whether the conclusion survives the translation. Which brings us to the last thing on this list. There is a number that circulates widely, and it needs to be handled carefully rather than repeated. Take the total mass and energy contained in the observable universe. Calculate the radius at which that much mass would form a black hole. The answer comes out on the same order as the size of the observable universe itself. Tens of billions of light-years, matching to within a factor that is small enough to be interesting. That coincidence is real, and the conclusion usually drawn from it is not. Here is why. The universe has very close to what cosmologists call the critical density, the density at which its geometry is flat rather than curved. That is a well-established observational fact with a well-understood explanation. And it is a matter of straightforward algebra that any universe at the critical density produces this arithmetic. The equation that gives a black hole's radius in terms of its mass and the equation that gives the critical density in terms of the expansion rate have the same structure, so the two numbers come out alike in any universe of this kind, whether or not anything is inside anything. So the coincidence does not show that we are inside a black hole. It shows that our universe has the critical density, which we already knew. But there is a weaker statement that survives, and it is the one this episode ends on. Nothing in current physics forbids the interior of a black hole from being a region with its own expanding geometry. That was the proposal mentioned at number 2, worked out by Frolov, Markov, and Mukhanov in the late 1980s, and it does not require any exotic ingredient beyond the kind of high-density behavior cosmologists already invoke for the first moments of our own universe. Lee Smolin built an entire framework on it in 1992, in which universes give rise to new universes through the formation of black holes, and the constants of nature are what they are because those values happen to produce a great many black holes. That proposal is unusual among cosmological speculations in making a falsifiable prediction, and people have tried to falsify it. Smolin's reasoning runs like this. If new universes are produced inside black holes, and if each new universe inherits its parent's physical constants with small variations, then the process has the structure of natural selection with black holes as offspring. Over many generations, the constants that dominate will be the ones that produce the most black holes. So we should expect to find ourselves in a universe whose constants are close to optimal for black hole production, not for life, not for stability, not for anything else, but for that. The prediction that follows is specific and checkable. Small changes to the constants should reduce the number of black holes produced, not increase it. Smolin identified several tests, the most quoted involving the maximum possible mass of a neutron star. If neutron stars can be considerably heavier than his framework allows, then a route to producing more black holes exists that nature is not taking, and the argument fails. Measurements of massive neutron stars over the past 2 decades have pushed hard against that bound, and whether the prediction has actually been broken is still argued about. Whatever the verdict, the structure of the proposal deserves respect. It takes an idea that sounds like metaphysics, universes inside black holes, and attaches it to a number that an observatory can measure. And nothing in current physics forbids a 3-dimensional world from being an encoding of information on a 2-dimensional surface, because that is precisely what the one case we can solve exactly says is true. Neither of those is established. Both are taken seriously by serious people, in print, under their own names. Put them together, and the honest answer to the question this episode began with, what is hiding inside a black hole, is not a place and not an object. It may be a description, a pattern held on a surface of the same general kind as whatever pattern holds the room you are lying in. It is reasonable to ask what could ever settle any of this, given that the subject is defined by being unobservable. The answer is less bleak than it sounds, and it is worth ending the substance of the list on it, rather than on a shrug. 3 things are moving. The gravitational wave detectors are improving, and each new merger tests the geometry just outside a horizon more precisely than the last. A deviation from the predicted ringing would be the first direct evidence that the classical picture is incomplete. The imaging arrays are being extended, with proposals to place radio dishes in orbit or on the moon, which would resolve the nested rings described at the start of this list and test the shape of the shadow against what rotation predicts. And on the theoretical side, the island calculations are being pushed, year by year, out of the idealized setting where they were derived, and toward geometries closer to the one we actually live in. None of those will produce a photograph of the inside. Nothing ever will. But the interior is not sealed off from evidence entirely, because a wrong interior produces a wrong exterior, and the exterior is measurable. Every one of the proposals on this list, if it is correct, leaves a fingerprint somewhere on the outside, in the ringing after a merger, in the shape of a shadow, in the statistics of a population of objects. That is how this subject will move, and it is how it has always moved. Look back at the whole descent for a moment. We started at a ring of trapped light, an infinite stack of images of a sky that no longer exists, sitting outside the horizon, holding the entire history of everything the black hole has ever been able to see. At the time, that seemed like a curiosity at the boundary, the outermost consequence of the object, a nice thing to have photographed. It was the first hint. The record was on the outside. It was on the outside at number 10, in light. It was on the outside at number 8, in entropy, 1 bit per 4 Planck areas. And it is on the outside at number 1, where the interior turns out to be the surface, read a different way. Every entry between them was an attempt to say what is in there. The strongest framework we have answers that the question has the wrong shape. That is not a disappointing ending, though it can sound like one. A countdown that arrived at a monster in the basement would have been a smaller thing than this. What the descent actually found was that the most carefully guarded interior in the universe keeps its contents where anyone can see them, and that the guarding was never the point. The horizon is not hiding anything. It is holding it up. Whatever else is true, this much is, the boundary of a black hole is not a wall around a place. It is closer to a page. And the deepest thing anyone has found inside one is a suspicion that the same is true of everything else, including whatever is holding you up right now. That is the end of the list. And it is a good place to leave it, with the strangest object in the universe turning out to keep its secrets on the outside, in plain view, in a script nobody has finished learning to read. Sleep well and good night.